Hello friends, let's have a look at the complex number together. So the first part is going to be something to get used to the forms, right? So the whole point of learning the complex number is to learn how to build a bridge between numbers and the geometry, right? So that whole connection is done by the complex number, and we're going to use a lot of application of a trigonometry and vector. So please fasten your seatbelt and let's enjoy the complex numbers, okay? So yeah, let's have a look at the first problem here. So this is a very typical problem. It's asking you to find the tangent pi over 12. So using the complex number, getting the exact value of a trigonometric value such as a cosine pi over 2, sine pi over 2, or tangent pi over 2, or cosine 7 pi over 12, etc., etc. Those are very popular. And that is to associate with the forms of a complex number in the Cartesian form, and then the polar form, compare between their modulus, so the real and imaginary part. So let's have a look at that one here. So now I'm given the u being the 1 plus root 3i, right? So for that one, what I like to do is to convert into the polar form. So it's going to be, well, you know, from now on, this should be very straightforward. You should know how to work with the converting the form straight away. So it's going to be the modulus is 2 cis, and then tangent theta is root 3 over 1, so the argument is going to be simply pi over 3, isn't it? So that is lovely. And so for the second one, that's going to be square root of 2 cis pi over 4. So you got the argument, my friend, of the pi over 3 and then the pi over 4. Okay, so that is great. And what I want to do here is to, either add or subtract to induce the angle pi over 12. Okay, and yes, as you know, if we multiply, for example, the complex number, you realize that I can add the argument, right? So it's gonna be cis theta plus phi is the product of the complex number, and if we divide cis theta over cis phi, that's gonna be the difference. So that is lovely. So right, those are the things that we should know and be able to prove using the compound angle of a trigonometry, and obviously that can be asked for the question in the exam or the school test. And so what you want to do here is to realize that it's going to be given the pi over 12 when you subtract the argument. So that means you want to divide, right? So you want to divide these forms and then compare the real and imaginary part. So let's have a look. So if I divide, what I get here is that on the right hand side for the polar form, it's going to be 2 over root 2 cis. And then it's going to give you, what is it? The pi over 3 minus pi over 4. Right, so then I realize, if I rationalize the modulus, that's gonna be 2 root 2 over 2, it cancels out, and if you look at the argument, that's gonna be the difference between the pi over 3 and pi over 4. So that's 12 in the bottom, 4 and 3, so it's gonna be pi over 12. That is lovely. Okay, so that is what I have. And on the left hand side, if I rationalize this, so if I rationalize that, it's going to be, let me write it here, 1 plus root 3 over 1 plus I, but I'm going to multiply by the conjugate, isn't it? So it's going to be 1 minus I over 1 minus I. So, if you expand the numerator, what do you get? It's going to be, just a distribution. So that's going to be 1 minus I, and then what do you do? Root 3I, and then plus root 3. So that is great. Over, and then it's going to be just the the modulus square, so it's going to be what is it, the 2. So that's great. So for the complex number, please get accustomed to separate by the real and imaginary parts. So that's going to be 1 plus root 3, and then I'm going to factorize by I, and it's going to be, what is it, root 3 minus 1. Lovely. So that is what I've got. Okay. And then what you're going to do here is to separate by the real and imaginary part. So the real part here is going to be 1 plus root 3 over 2. And then the imaginary part, my friend, is going to be, what is it? Square root of 3 minus 1 over 2. And that should be equivalent to the real and imaginary part of the right-hand side. So if I beautifully expand, it's going to be square root of 2 cosine pi over 12 plus I square root of 2 sine pi over 12. So now you can compare the real imaginary part to get the respective cosine and sine value, where you can use for the tangent. Okay, so please make sure every time we got a complex number problem and somewhat asking you to find the value of a cosine, sine, or even tangent, that is something to do with the operation of a complex number, either multiplying or dividing, and compare with the real and imaginary part. And for the tangent, I need both of them, so then you use both of them to get the tangent pi over 12. And obviously, you could have used this as a compound angle for the tangent, but that's not the spirit of this question because they ask you to use the complex number first. Okay, so that will be the first question that we can try using the forms of a complex number. Let's move on to the next one, my friend. Oh, wow, so it's going to be proof by induction. So, you know, what do we do? It's really the proof of the DMT, isn't it? The De Moivre's theorem. So, yeah, you know what, let's try it. So, you know, so sure, it's going to be for the positive integer. So I'm going to write n equal to 1, okay? So then I'm going to work with the basic step and see if it's going to be equivalent between the left-hand side and the right-hand side. So it's going to be 1 plus root 3i. So that is the left-hand side. And then I'm going to compare with the right-hand side, my friend. I'm going to just plug in the n equal to 1. So it's going to be 2 cosine pi over 3 plus I sine pi over 3. And as you realize, you know, that's going to give you, what is it? So, you know, please be master of a trigonometry. So those special angles you have to memorize. So it's going to be 1 over 2 plus root 3 over 2i. So if I distribute, my friend, I get 1 plus root 3i, and that's lovely. So that they are equivalent, so I'm very happy. Okay, so that will be the basic step. Okay, so then I'm going to erase everything. So now for the induction part, we know that I have to prove the significant part of, what is it? The induction hypothesis implies the result to prove. So here's the thing, I cannot use the result, but I know that I'm heading there. So for the induction, it's not that bad because you already know the answer. You already know the answer. The whole point of doing the induction process here is to show which step you can take to get to that stage, right? So I'm going to write two things here. So I'm going to write, okay, the induction hypothesis here must be, what is it? The 1 plus root 3i to the power of k is equal to 2 to the power of k times cosine, well, you know, I can't be bothered, so I'm going to write as a cis, okay? I hope you don't mind. So I'm going to be, what is it? I'm going to do the cis k pi over 3, voila. That's how I'm going to do it, okay? So then the result to prove, my friend, the RTP is going to be exactly the same thing, but just to raise the power of k plus 1. So you know what? I'm going to duplicate this, my friend. That is great. Then I'm going to just raise the power by 1, like that, okay? Then it's going to be plus 1. Then the argument, I have to simply show that it's going to be k plus 1 pi, okay? But yeah, you know what? This raising power is very popular for the induction. So obviously we have to use the induction hypothesis one way or the other. So what I'm going to do is to choose my side to be starting from the left. So yes, this is equivalent. So either you can start from the left to the right or right to the left. But I prefer working with the left in this form here because I can use the induction hypothesis well. So that one, for the multiplication with induction, is to use the power rule, right? So it's going to be the same as by the multiplication property, 1 plus root 3 I to the power of k, my friend, is going to be multiplied by the power of 1, isn't it? So that is what I have, right? So that is great. And then what you have there is what so then I would use the induction hypothesis to substitute. So that's lovely. So let's use that. So I'm going to put that into the induction hypothesis in the cis form. So that is great. And then I'm going to multiply that by who? The Cartesian form, but obviously for the complex number, we prefer working with the, what is it? The same form. So because I convert it to the modulus argument form, I'm going to do the same thing for the second form. So it's going to be, what is it? Oh la la, it's going to be, you know, so it's 2 cis. The argument is pi over 3, that's lovely, and as we know, for the complex number, if you multiply, you are going to simply add the argument, isn't it? So the modulus is going to be raised to the power of 1, so it's going to be 2 to the power of k plus 1, and then cis, I'm going to add the argument by pi over 3, so that's going to be k plus 1 over 3 pi is what I've got. So you managed to show the result to prove, so that is great. Okay, but here's the thing, for the induction, do not forget to comment on the conclusion. So induction is typically from 6 to 9 marks, but I would say this is always categorized into 3 different fields. Whether you can show the basic step, whether you can show if we assume the induction hypothesis to be true, is the result to prove also the true. So you got to show the second stage, and third stage is all about the conclusion. So what we can say is, oh, we managed to show the basic step works, induction hypothesis implies the result to prove, hence the statement must be true for the all positive integer by the principle of mathematical induction. You have to write down those conclusions. That's the key of the assessment of the induction. Okay. All right, let's have a look at the next problem here. It's talking about the complex equality. It's always about the real part versus the imaginary part if it's in Cartesian form. So let's have a look at this. So find the possible values of A and B. What we're going to do first is to expand on the left-hand side. And then you're going to put them in the real, imaginary part, perform the simultaneous equation. When you read a question like this, I don't want you to jump into the computation yet, but please try to think about the steps that you want to take. So when I'm looking at this, I know it's going to be talking about the complex equality. That means I'm going to compare with the real and imaginary part. Then you realize, for the Cartesian form, it is very likely to work with the simultaneous equation, right? Those type of logical process is something that you need to practice before doing any computation. That will be the first half of achieving good marks on the complex number or in math in general. But the second part is how quickly you're going to be able to compute and accurately. Okay, so let's have a look. So for this one, I'm going to expand on the left-hand side, right? So it's going to be a squared minus b squared plus 2abi. I want you to notice that I just group by the real and imaginary part right away. And I'm going to compare with this right-hand side. So that suggests that my real part, a squared minus b squared, is going to be equivalent to negative 16, where 2ab, the imaginary part, is going to be equivalent to negative 30. So that is great. Okay, so my real part here is going to be negative 16. My imaginary part here is going to be negative 30. So that is great. So now it's just really the time to do the simultaneous equation. And for the algebra, I prefer simplifying before anything. So if you divide by 2, that's going to be 15 on the right hand side. So that is lovely, right? So then on this one, it's going to be b is equal to negative 15 over a. So that is great. So what you want to do is to substitute that in here. Okay, so if we substitute that, I'm going to get, what is it? The a squared and plus 225 over a squared is equal to negative 16. Oh, that is great. Then you can do the, what is it? The multiply by the a squared and to work with the quadratic equation, even though it's in a quartic form. So if I multiply by the a squared on both sides, I got the a4 plus 16a squared plus 225 is equal to 0. Then you can solve this by, what is it? Solve by factorization, right? So because even though it's degree 4, you realize if you let the a squared to be t, then it comes down into the quadratic form and you should be able to find the a. And if you found the a, then you can use a substitution on here to find the respective b. Okay, so what I want you to do here is there's a lot of equality number in the complex number. Starting with the Cartesian, you can do the modulus argument form as well. We're going to have a look at that. That's a little different because that involves the trigonometry. However, for the Cartesian form, it's very likely to work with the real and imaginary part. Let's move on. So the answer should be 3 and negative 5, and I want you to check. Okay, so let's have a look at the second part here. So yes, you're going to get a lot of the complex number in the bottom, in the denominator, but I want you to be, whenever you see, I see complex number in the bottom, in the Cartesian form, please remember to use the following form. So I want you to use 1 over z. If you multiply by the conjugate, I do realize it's going to be conjugate on the top, but as I have mentioned before, if it's a product of a complex and a conjugate, it's just a modulus square. So we're gonna put it into modulus of z square. So that is what it is, right? That is what it is. So then I can do that conversion very quickly. So like I said before, you already know that this is somewhat working with the complex number with algebra. So a lot of arrangement, right? Rearrangement and simplification. But in particular for this one, I got the complex number in the bottom. So I know that I'm gonna use that form and try to solve it as quickly as possible, accurate as possible. So let's do it. So let's go. So if I use that form right away on the first part, I know that's going to be simply just 3 minus 4i over 25 times z. So that is lovely, right? So for the second form, that's going to be, I'm going to just multiply by the I, right? I don't have to necessarily multiply by the negative I for the conjugate for that matter. So it's going to be negative, what is it? Z minus 1i over 5. That is great. And on the right-hand side, if you multiply by the conjugate, that's going to be 5. 3 plus 4i over who? 25. Boom. Okay, that is great. Then yes, you're right. So now I don't want to work with fraction, and I can simply multiply by 25. Okay, so if I do a boom, boom, and then if I do the distribution here, my friend, what am I going to get? I'm going to get 3 minus 4i, z minus 5, z minus 1i is equal to, boom, 15 plus 20i. Right, so that is lovely. And from this, what you can do is, my job is to find z. And that means you're going to factorize it with respect to z and trying to rearrange. And so I'm very happy. I'm very okay to factorize everything by z. And maybe I can bring the z, another z from the second term, but not entirely, right? I just have to get the negative 5, right? I just have to get the negative 5 and then put it where, my friend? Right there. So it's going to, negative 4 will be raised by negative 9. Well, raised, but change, right? So it's going to be, what is it? It's going to be 3 minus 9i z. That is great. Okay. On the right-hand side, well, the constant part, as long as it's not in multiple of z, they can just stay, no problem. But as you can see, you know, so from the second form here, I took out negative 5z, put it into the first bracket. The remaining should be then shifted to the right-hand side. That would have been positive 5i, but I shifted to the other side. Minus 5i is what it is, right? So that is great. So for that one, it's going to be 15 factorized 1 plus i. Okay, so I'm very happy because now I can just rearrange to get the z, isn't it? So if I just rearrange, then, you know, the z is going to be 15, 1 plus i. That is great. And on the bottom, I factorize by 3. So that's going to be 1 minus 3i. Is what it is. And then I'm going to multiply by the conjugate. That's going to be 1 plus 3i and then 1 plus 3i on the top. So that is great. And put the I there. Then you're gonna do the, you know, distribution. So it's going to be simply 5. That's going to be simply 5 and then 1 plus I on the bottom. That's 1 plus 9, so that's 10. And I'm going to multiply 1 plus 3i. So the only thing that I have to really distribute is just this 2 here, because that becomes just half. And if I expand, it's going to be 1 plus 4i minus 3 over 2. Negative 2 over 2 would be negative 1 plus 2i is the simplified form. So, you know, I don't have to, you know, what you could have done here is to let z to be x plus iy and then try to compare with the real imaginary part. But I don't have to because I can just put whole chunk of the forms as long as I'm more familiar with how to convert things out with the product of complex and conjugate. And those operations in the Cartesian form, you got to be very, very comfortable. Okay. All right. So yeah, same thing here. You know, I got the complex number in the bottom. So what I can do is to use it, right? So, and then, you know, not necessarily am I going to put the, I mean, I am going to, but I don't have to start with that, you know, so that's the complex number I got to put, but I don't necessarily have to put it there because as soon as I see in the bottom for the complex number, I know that I'm going to multiply by the conjugate, and you know the product of complex conjugate is what? Very good, the modulus square, isn't it? So I am going to convert this right away as what? So the numerator is going to be 25 z conjugate over, that's going to be the product of complex and conjugate. So it's going to be a modulus square, that's going to be 4 times 5, so that's going to be 20. you see, minus, what is it? The second one is going to be 15z over, it's going to be the same thing, isn't it? So 4 times 5, so that's going to be 20. So that is lovely, right? So that is what I've got. And then I want to simplify on this one. So that's, but on the left-hand side, if I factorize by 5, that's going to be 5 over 4 z conjugate minus 3 over 4 z. Okay, now I can put the z as x plus iy because it's very simple to group, very simple to work with the real and imaginary part. So if I multiply by 4 on the right-hand side, I have 4 minus 32i. So that's great. Then I'm going to let the z to be x plus iy. For the z conjugate, if I do the distribution, that's going to be 5x minus 5iy. If I multiply by negative 3 on the z, it's going to be negative 3x minus 3iy. And I'm going to group by the what? The real and imaginary part. So it's going to be, what is it? Boom, boom, 2x. That's lovely. Minus 8iy. So therefore, I know that x has to be 2, y has to be 4 by using the equivalence of the complex number comparing the real and imaginary part. Okay, so that is great. So those are working with the, what is that? The Cartesian form. But of course, we want to associate with the modulus argument form equality. And that is going to use a lot of the trigonometry. You're going to use a lot of trigonometry. So trigonometry. So to be honest, okay, I don't know why they have put the complex number in the topic 1. Because yes, it is algebra, huge algebra. But I think it should have been, could have been separated. Okay, the complex part 1 in topic 1 for the algebra to associate with just the forms like this, I guess. And then topic 2 with complex number and polynomials. And then that can extend to the fundamental theorem of algebra. So I wish they could have added more of the complex number with the locus point to associate with the conic section like the ellipse, hyperbola, so that you can extend the hyperbolic function with the complex number. And then topic 3 with the geometry and then the complex number so that they can focus more on the, what is it, the vector and trigonometry and then the other shapes. But I don't know why the whole chunk was just put in topic 1, but that's the tradition. Let's get stick to. So here, I got the polar form, and then that's my job to convert into the cotangent theta over 2. And for this one, I want you to remember several operations in the modulus argument form. We already mentioned about what the product and then the quotient, and how we can then use the argument to combine them. Product was the sum for the argument, and the quotient was the difference of the argument, just like the exponential function, hence the exponential form to associate with the complex number. But also what I want you to remember is the sum of a complex number, which appeared in May 2022, for which that I was very proud to predict, okay? Anyways, let's have a look. So suppose I've got the cis theta plus cis phi. So that is lovely, right? So for that one, what I want you to do is to memorize the following formula. You should be able to prove it either using the trigonometry or vector, but for simple calculation here, let me just quickly write down the formula. That's going to be 2 cosine theta minus phi over 2 cis theta plus phi over 2. Yes, I do strongly encourage you to memorize this and be able to prove it either using the trigonometry, especially the use of a sum to product, from the compound angle, or vector by sketching the rhombus. But anyway, so if I then use that one, then this one becomes pretty simple. So 1 is what, my friend? Cis 0. So on the left-hand side, if I quickly simplify the left-hand side, that's going to be cis 0 plus cis theta. Do you agree? Very good. And for the denominator, that's cis 0. But here's the thing. I prefer working with the sum. So even if I have a negative z, I'm going to convert that into the modulus, a positive modulus, by converting the negative 1 as a cis pi. So that is great. The z was a cis theta. So if I do the product, you realize that it's going to be just the sum of the arguments. So it's going to be cis theta plus phi. That is lovely. So that's the one I have on the second term on the denominator. So I'm going to duplicate that. So that is great. Okay. Okay, so I'm going to add them together. But, you know, the addition is, what is it, commutative. So I can just put that on here. Well, just for the convenience. You don't have to, as long as you realize that it's commutative. So I'm going to shift it there. Okay. Yeah. And then for the second term here, put it here. Yeah, you don't have to, but you know, for the convenience of the computation and just for the look of it, it's just better to have something non-zero at first, because well, you know, cosine is an even function, so it doesn't matter which one you subtract actually, but it looks prettier. So then I'm gonna use the top and bottom, right? So the numerator, if I use that formula here, the sum of the complex number, that's going to give you, what is it, 2 cosine theta over 2. That is lovely. Cis theta over 2. So that is great. Over. Now I'm gonna do that. So that's gonna be 2. The difference still 0, doesn't do anything. So cosine and theta over 2 plus pi over 2. And then cis theta plus pi over 2. Okay, so here's the thing, you know, I want you to realize why I would have actually separated for the first one, especially for the cosine, because every single time you see something of a pi over 2, what angle do I want you to remember? I want you to tell me. Every time you see the sine or cosine or tangent with the pi over 2, what do you have to remember? Can you tell me the type of the angle? Very good. Either the complementary angle or cofunction identity. That's how they call it. It's going to convert into the sine. You should know it very well from the extensive study of trigonometry. Reference angle, supplementary angle, complementary angle, cofunction identity are very, very important angle formula. So here it's going to be just converting into sine theta over 2. You should know how to prove it, not just using the compound angle, but also using the circle. Okay, please be able to prove all the identity using the unit circle. It's gonna be very popular for paper 3. Okay, so we can cancel those two out. So that is great. So I got the cosine over sine, which is the cotangent. So that's great. I got the cotangent theta over 2. That's great. And for the complex number in the polar form, if you divide, you already know you're gonna simply subtract the argument. So I'm gonna look at the difference of the argument. So it's gonna be cis negative pi over 2. And then you know that the cis negative pi over 2 is where, oh, hold on a sec. Is negative I. Have I done something wrong? Give me 1 second. I think this formula is correct. And that was a cis pi. So it was a cis 0 plus cis theta plus pi. I get it. But its addition is commutative, so it's okay to rearrange the order. And then I look at the sum and difference over 2. So I got the theta plus pi. And then I'm subtracting. Is this negative pi over 2? I think it's negative I. Okay. So, you know, I'm filming, so, you know, I just want it to be flowing. I don't want to go back and think, oh, which one have I done? If you found where I've done wrong, please comment. But I think it should be negative I cotangent, I think. Okay, but anyways, you know, the whole point of, I think the whole purpose of this problem here is to use this one well. Should we do the double check? Let's just do the double check. So negative 1 is cis pi. So cis pi times cis theta gives you cis theta plus pi, which I have. It was a cis 0 plus cis pi plus theta. It's okay to switch because there's a commutative. And I'm using that formula. It's going to be 2 cosine difference over 2, sum over 2, but it's 0. Doesn't matter. Doesn't affect anything. That's great. And what I'm doing here is, oh, I know where I've done wrong, okay? Sorry. I know where I've done wrong. So my bad, my friend. So yeah, it is a complementary angle. It is a complementary angle, so it will convert into the sine. However, you gotta be careful. Okay, so it's so now you gotta be careful because I go pi over 2, and then I'm adding some angle. So for the cosine, it's located in the second quadrant. Doesn't matter if it's acute or obtuse. In fact, the result is gonna be the same. It will come out to be negative. So while converting into the sine, Now you're going to multiply by the negative because the initial value would have the negative value there. So here this is going to be in fact negative sine theta over 2. Okay, so that's where I got it wrong. So it's going to be double negative. So it's going to be in fact, what is it? Positive. So the answer is correct. Okay, that is great. So that's going to be, so, you know, for example, if I quickly give you another example with the complementary angle, sine, you know, let's go 11 pi over 2 minus theta. How is that? Okay, so every time I have odd pi over 2, my friend, that's gonna be the complementary angle. So no matter what, I'm just gonna convert into cosine theta, no matter what. But what you need to be careful here is to choose the coefficient, whether it's going to be positive or negative. Let's check. So if you think about 11 pi over 2, you just have to really think whether it's going to be above or below. Okay, so that's, you know, on top of 5 pi, I added pi over 2 further. So I'm located between the third and fourth. But I subtracted by theta, which I send to the third quadrant. And in the third quadrant, only tangent is positive. So sine must be equipped with the negative. So this should be negative cosine theta. So that's how you get to convert between the, you know, complementary and reference angle. Okay, so very lovely problem because not only the product quotient also gives you sum of a complex number and how to combine. And we know how to simplify using not only the operation of a complex number, but also trigonometry, especially the complementary angle. So if you revise well for the complex number, you already have done topic 1 and 3, you see. So this is a very, very good topic to revise for the trigonometry, as you can see. Okay, so let's have a look at this part here. But before I do, let me take a 5, okay? And then come back to you in 5, okay? See you in a bit. Hello, so let's have a look at this example now after my break. So for this one, I put this on the slide because yes, this is a very typical Cartesian form, right? So yeah, you know what I think they would have expected to is to put the x plus iy there and then, you know, work with the conjugate and all that. So that is great. However, you know, I think this question could have been also done by just simply cis theta, right? Imagine instead of working with the Cartesian form, that you would have worked with the cis theta. And for that one, for me, I think would be also a very lovely problem because you realize that it's going to be cis theta, and I got the 1 plus cis theta here. And as you can see, that's not good because it's not in the modulus argument form yet because it's not put together. But because of using the technique that we just talked about, that's going to be cis theta over cis theta plus, and then the 1 is just a cis 0. So that is a great, so I can work with the combined form. So that's going to be cis theta over, and you know, now I'm going to use the vector form here. It's going to be 2 cosine theta over 2 cis theta over 2. Right? That's great. So for this one, then I realize, okay, so I'm going to have, what is it? The modulus being the 1 over 2 secant theta over 2. And then the argument here is going to be just to find the difference here. So it's going to be simply cis theta over 2. So for me, my argument is going to be that. And if you wanted to have the imaginary part, then I would just take out the sign and that's it, right? So and then put it in the product with the modulus. But yeah, so just wanted to show you that every time we have something with the complex number, you can combine them together using the form that we just talked about, right? So yeah, that's also a lovely problem here. There are many ways of proving this, okay? Either by sketching, you know, like things like that. But for me, let's try to work with the algebra. So the algebra I want to talk about here is that while we talk about that, I want to talk about the absolute value. So in the exam, you know, you're going to have 3 forms of the absolute value. So, and then our enemy is to get rid of the absolute value. So every time I have absolute value of x, where x is a real number, and how we got rid of it is to square it. So modulus of x squared is simply just x squared. So that's great, okay? That's number 1. And then the number 2 is if I have a vector, right? And that vector, let's say, is in n dimension. And if you want to do the modulus of the vector is to talk about the magnitude. And if you square it, then you know it's just the dot product of itself. Okay, so that's how we also convert the absolute value on the vector, which we often see in the topic 3 problem. And then the next thing I'm going to talk about is to talk about the complex number, right? In the complex number, if you do the modulus of z squared, that is going to be equivalent to the product of complex and then conjugate. So I want you to make sure you just try to use these three depending on the forms. And here we got the absolute value, so I know squaring it can play a vital role to solve such problems. And if I square this and realizing that this is what number, right, is a complex number, then makes you convert into the product of the complex number and its conjugate. I'm not going to do the perfect square here like a real number or any variable. So here what I can do is that you realize that it's going to be simply the product of the complex number and its conjugate. And then, what I want you to remember, like I said before, I emphasize this also. If it's Cartesian form, then yes, you just have to put what is it, and the minus sign on in between the real and imaginary. However, this is not a Cartesian form. This is just a complex number, and the conjugate will be just distributed like that. Okay, so make sure you don't confuse yourself with the complex number and its different forms, such as the Cartesian form, especially when you're dealing with the conjugate. Okay, so that is a great. So I'm gonna have equality here, and I got the difference there. So that is what I have. Okay, so on this one, what I want to do is then to expand it, right? Then I'm gonna expand it. So if I expand here, that's gonna be z times z conjugate plus what is it? It's gonna be z omega conjugate, omega z conjugate plus z conjugate, and is equal to, so that's the left-hand side, and I want you to realize is very similar to the right-hand side, isn't it? So the right-hand side only will differ by the middle part, so that's gonna be just the minus there, isn't it? And I think the right-hand side will be just positive, so that's the same thing, right? Oops, sorry, I meant to put the omega here, isn't it? Okay, so that's a good point. Thank you for correcting. So that is what I have, but still it doesn't change the fact that that's going to have the same sign, the left and right. So what I can beautifully do is just cancel them out. So that is great. And I'm going to maybe shift that to the other side. So if I shift that to the other side, you realize it's going to be just twice. So it's going to be, so then it's going to be, what is it? Maybe I will work it reversely. So what I mean by that is I'm going to put that on the left-hand side, and maybe I'll put that on the right-hand side. Okay, then you realize twice of the complex number z and omega conjugate is the negative, what is it, twice of the omega z conjugate. But I have a common factor of 2, so I can get rid of it. So that is a great. Okay, sure. And for me, what I can do is I will let the z to be cis theta and omega to be cis phi. How is that? And now I realize on the left-hand side, if you do the product with the conjugate, you realize here it's going to be cis theta minus phi, right? So that is a great. And on the right-hand side, where the -1 is what representing cis pi times, and it's going to be the conjugate of that version, so it's going to be cis phi minus theta, right? So that is a great. But on the right-hand side, you can simplify further by adding the argument, isn't it? So it's going to be cis pi plus phi minus theta is what I've got. That's lovely. And so for this one now, I want to remind you, if you have a complex equality, especially for the polar form, I don't want you to jump into the fact that the argument has to be the same. They don't have to, as long as it's just a 2 pi multiple, right? So if you realize cis pi over 6 is the same as cis 13 pi over 6 because it's in the same location on the Argand diagram, right? But that doesn't necessarily imply that the argument has to be the same. So remember, if you have a complex equality in the modulus argument form, the argument has to be what? Theta is equal to, sure, the phi plus 2k pi, where k is integer. So you have to remember that. That's how we distinguish between the argument there. So if I realize that, you realized, if I realize that I want to use it for the, let me erase this part. And then I'm going to use what just compare with the argument. I'm gonna you compare with the argument of theta minus phi, pi plus phi minus theta is what I'm going to do. So that's going to be theta minus phi is equal to pi plus phi minus theta. Then what I can do, my friend, is just group them together, right? So if I shift that to the other side, that gets double. It doesn't cancel out because they are the opposite side. So twice of the theta minus phi. Oh, oops, sorry. Don't forget to add by 2k pi. Yeah, that's what I had to say, right? Because that's the argument saying, right? And then you realize it's gonna be 2k plus 1 pi if you factorize by the common factor of pi. And if I divide by 2, you realize it becomes like that. And then you realize that whatever the integer you put in the k, you realize the numerator is going to be always, the numerator is always going to be odd pi over 2. So that gives you pi or 3 pi over 2. Either way, it's going to be always perpendicular. So from that result, the difference of the argument is going to be always perpendicular. Okay, so that's how you can also prove. Understood? So yeah, you know, for this one, there's many different approach. I think sketching is very nice on the Argand diagram. But you know, I use the algebra part just in order to show the absolute value in the exam. There are 3 times. You square them first, but how the outcome is a bit different. So for the real number, just a perfect square. However, vector, dot product of itself, complex number, the product of the complex and its conjugate. Okay, that is great. Let's have a look at the next part here. You know, for this one, it's just a Cartesian, so I'm sure it's going to be simply simultaneous equation. We have already done those type of questions, so let's try our best to solve different types of problems. Hopefully, maybe like the exponential form. So, and let's see. That's fine, man. You know. I like the last part, but I think there's a better one. Yeah, it's fine. Maybe that's a good one. Okay, so maybe this is a good one. So, sure. Should I do this? Okay, let's do this. So find the 2 squares of root of the. So you know, if I take a square root of that, and I want to find the x plus iy. Okay, and then as you can see, how you can do is just to get rid of the square root by taking the perfect square on both sides. Then you realize negative 5 plus 12i is equal to x squared minus y squared. What is it? Plus 2xy I. And then you're going to compare the real imaginary part, so that's absolutely fine. Okay, and then you can show this form using the operation. Okay, so I would strongly encourage you to prove this either by Cartesian form or the polar form. Okay, I will leave that as an exercise. But the reason, despite having the similar practice like that for the simultaneous equation, is to check on this part here. It says, hence, write down 2 square root of what? Negative 5 minus negative 12i. Okay, so I want to find this to be what? To be the p plus qi, and I'm supposed to find a pair of two sets of pairs of the p and q. Okay, so for that one, what we can do here is, okay, what I'm going to do here is maybe I would take the, the squaring on both sides. So let's do that. So I've got the negative 5 minus 12i, typically p plus qi squared. So you know what? You could have done, my friend, you could have done, the expansion and solve the simultaneous equation, maybe. But here it says hence. That means I really want to use the identity before, right? That's a must. If it says hence, despite having multiple ways of solving it, you really must use the previous information. And then the previous information suggests that I already know the form of negative 5 plus 12i. So maybe I would take the conjugate here, my friend. Okay, maybe I would take the conjugate here. So then I realize, okay, so that is going to be taking the conjugate on both sides. But what you just realized, my friend, is that from the previous information, squaring and conjugate can be switch around. It can be square and the conjugate. So on this one is going to be then I'm going to use p plus qi conjugate square is also what I can do, isn't it? But then I want you to realize, hold on a sec, that is simply, what is it? Negative 5 plus 12i, which I already have. Right, I already have the values on the previous information, supposedly using the simultaneous equation. So now you can use that value. So this is going to be the same as, what is it? The x plus iy squared. And then use the conjugate of that to find the p and q will be the answer. So the only reason I wanted to jump in this one is because some people found it very difficult to use this hence problem from the squaring and the conjugate. Okay, you could have solved this using the simultaneous equation, but that is not the spirit of this problem. We have to use the identity just before. Okay, but I really want to work with the Euler form. Well, I cannot skip this one. So let's have a look at this one. Sure, I want to find the modulus argument of it, but I want you to realize for the real imaginary part, we really want to convert into the cosine and sine. Can you please tell me how to convert the sine into the cosine form? Can you whisper to me? Very good. There are many identities, namely two are very popular, Pythagorean identity or the complementary angle. But here we're going to just switch around the argument. So it's going to be cosine pi over 2 minus theta plus I sine pi over 2 minus theta. Okay, so that is lovely because now I can use the real and imaginary as a cosine and sine. So that is going to be this pi over 2 minus theta. So that's great. Okay, so that's how we're going to solve it. And for this one, sure, let's have a look. So modulus is going to be, what is it? Two things, square root of ROU, 1 plus tangent square. But by the Pythagorean identity, that's a secant square. So I'm going to put it as a square root of a secant squared theta. But, it's modulus, and it's a square root of x squared. Is the absolute value of a secant theta, please. It's the absolute value. Do not forget to write that down. So, and then the argument, if I call the argument alpha, that's imaginary part over the real part, simply tangent theta, then boom, argument has to be theta. So this one is simply going to be absolute value of a secant theta times cis theta is what we're going to use. Okay, no problem. I think the next one is a very, very popular, so make sure you're able to simplify this one as much as you can, because by the disguise of a complex number, it's really the topic of a revision and extension of trigonometry. So you should be very, very good at trigonometry when you start working with the complex number, especially the polar form. So here, let's have a look at the modulus here. It's going to be square root of ROU, 1 plus cosine square plus sine square. So I smell the Pythagorean identity, isn't it? Because of sine and cosine. So if I do, it's going to be 2 plus, 2 cosine theta. So I got rid of it as a 2, factorized by 2, 1 plus cosine theta. But here's the thing, you could have left it there. So sure, however, every time I see a pair of the cosine and the positive one or negative one, I can really get rid of it using the double angle. So you should really be thrilled to see cosine in a pair of paired up with the positive one or negative one. So for me, I'm gonna let cosine theta in this case as a cosine 2 times the theta over 2. And that's going to be same as, among 3 of the double angle form of a cosine, the one that contains a negative 1 will nullify the existing positive 1. So I'm going to use 2 cosine square theta over 2 minus 1. That is lovely. So here, I'm going to get square root of 2 times 1 added by the double angle version of the cosine here. And just like that, I'm going to replace it. Okay, so that is great. So I'm going to cancel it out, right? Then I'm happy because it's a 2 squares. So the square root will indicate that I will have 2. Absolute value of square root of cosine square will be absolute value of cosine theta over 2. So that, my friend, is going to be your modulus. So that is your modulus. And how do I find the argument? If I let the argument of this complex number to be, let's say, phi, then I know tangent phi has to be the imaginary part of the real part. So it's going to be sine theta over 1 plus cosine theta. But here's the thing, you should, like I said before, you should be really, really comfortable with the trigonometry in a way that you see this one and then realize what identity you must use. You must be able to come up with, because it's a very, very popular identity, and it is going to be popular for paper 1 and paper 3 for integration by substitution using the trigonometric identity. So please learn it. So that is just simply the half angle of a tangent. So that, theta. So that's just the half angle of a tangent. So then phi must be theta over 2. So that's how we're going to simplify. So for that one, it's going to be the modulus is 2 absolute value of a cosine theta over 2. And then I'm going to multiply that by who? Cis theta over 2 is how we're going to write. Okay? That's good. So yes, it's just a revision of a trigonometry. That's what it is. Okay? So sure, find the polar form of that. Oops. Let's have a look at that. So, the modulus, I will leave it as an exercise. It's pretty trivial to prove. So I want to just change into the argument. So let's try to find the argument of this. So then if I let the argument of that to be phi, then I know tangent phi has to be the imaginary part and the real part, isn't it? So it's going to be negative. Oh, okay. Interesting. Over 1 minus cosine 2 theta. Oh la la. It was 1 positive cosine theta in the denominator that will induce the half angle of a tangent. But in this time, I really encourage you to be able to prove it because it really goes over the double angle identity thoroughly to derive it. But this is the half angle of a cotangent. So this is going to be negative cotangent theta because it's half angle. The 2 theta now gets into half of theta now. Okay? So sure, so now I got the tangent theta to be negative cotangent theta. And then what you realize is that this really doesn't help because of two things. I got the negative and the cotangent. Not only does it have the negative sign, but it's not something of a tangent that I can't use the inverse tangent. But I want you to realize, is it cotangent even function or odd function? Very good. Cotangent is odd function. Please be able to prove it, okay? And since it's odd function, this negative can actually go inside. So it's going to be cotangent negative theta because it's odd function. And also now you realize I have a problem. I don't want to work with the cotangent. I prefer working with the tangent. What does that imply? Absolutely right. If I want tangent, okay, I should convert the cotangent into something of a tangent. And what formula does that remind you? What angle form? Yes, the complementary angle. So you do realize that the cotangent theta is tangent pi over 2 minus theta. So that one actually with the negative here, it's going to be theta minus pi over 2. Sorry, tangent theta minus pi over 2. So that is great. Why? Because now I have a beautiful tangent equivalence here. The argument will be simply theta minus pi over 2. So that's great because then the argument here is going to be theta minus pi over 2. Okay, so this is really the simplification of the trigonometry using many identities as quickly as possible. Okay, so yeah, this is very similar to. So I want to find the argument of this complex number. That means you want to really convert the inside the first. So it's going to be tangent phi. If I let the argument of that form, whatever, it's going to be the imaginary part, isn't it? So 1 minus cosine theta over sine theta. If it doesn't ring a bell right away, every time you have this sort of a, 1 plus minus cosine, 1 plus minus sine, I think it's a great idea to multiply sort of a conjugate, meaning the plus minus negative on top and bottom. So if I do 1 plus cosine theta, you then get the difference of a square, which I have the 1 minus cosine square, for which you can extend to the Pythagorean identity. So the numerator will be simply sine squared theta. And the denominator will be sine times 1 plus cosine. But you realize, oh, hold on a sec, it's got the common factor. So I got the sine over 1 plus cosine, for which you realize it's again the half angle of a tangent. So that's great. So for this one, whatever the modulus was, it's going to be cis, and then the argument will be theta over 2. And I'm squaring it. And using the DMT, you realize that's going to be simply just r squared cis theta. So that's how we can prove things and very, very quickly like that, okay? So far, so good. So as you can see, a lot of revision with the trigonometry. Yeah, this is very trivial, right? So for this one, just conjugate. So cis negative pi over 4, and I'm squaring it. Please make sure that you use the DMT. If it's multiplication, you're adding the argument. If you're subtracting the sorry, if you're dividing the complex number, you're subtracting the argument. So this is actually a lot simpler than the ones we have done so far. So I wouldn't go over it. Okay, so it's pretty simple. Oh, well, yeah, you know, it's got the gem here. But then I will go over that once we start talking about the application of complex number. This session here is really just working with the forms between the Cartesian and polar and then the Euler form. Where is it? Yeah, you know what? This is actually quite important. So let me quickly show you this one. So yeah, you know, so as soon as I have, you know, something with the Cartesian form, it's got the division and says that for real number, okay. I'm going to put something to the power of n, you see? And I do not like working with the power with the Cartesian form because you got to use the binomial expansion a lot. And we don't like that. We want to use the DMT because then we just have to touch the argument, that's it. So let's have a look. So for this one, it's going to be 2 cis pi over 3. This is a root 2 cis pi over 4. And what we're going to do is to look at their the quotient form. So on the numerator, that's going to be simply root 2 cis voila pi over 12. So that's something that we had done at the very first example, isn't it? So now I'm going to put it into the power of n. So let's do that. So if I put it into the power of n, and then I'm only talking about the real number. So I'm not really concerned about the modulus. That's just the size of it. But only the argument will determine. Only the argument will determine whether it's going to be purely imaginary, purely real, okay? And I want positive, find the smallest positive integer so that it's going to be a real. It's going to be a real. So yes, as you know from the Argon diagram, if you want, my friend, to, something to be what? Real, it needs to be integer pi, isn't it? If it wants to be a real, it needs to be integer pi. So I know n pi over 12 has to be integer pi. So that's what it is, isn't it? Okay, where k is integer. So my job is to find the n. So I'm going to get rid of the pi. So n has to be a multiple of 12, right? So that is great. And you know, for the least positive, so it shouldn't be 0. So k being 1 will give you the answer. So n has to be simply 12. And you know what? Sometimes they ask you to find a positive real. It asks you to find a positive real. So for that one, what you have to be careful here is that if you put k equal to 1, you get a pi. You get cis pi. Cis pi is a real, but it's not positive because it's a negative. You see? So if you want the positive real, not only should you put that as a k pi, but you got to put the even pi. So it's going to be, the equation should be then converted into, if it was a positive, then I would have done the n pi over 12 to be 2k pi. It needs to be even pi to guarantee that it's going to be positive real. So for that one, n being 24 is going to be, would have been a great answer, okay? So it depends, you know, there's a subtle difference there. Sometimes they ask you real or positive real, so you have to read it carefully. Okay, so that is also working with the complex equality. It's fine, you know, so I really want to get into the Euler form. So let's have a look. So those forms we already have done enough, so that's okay. There you go. So yes, Euler form is given as such. Yes, it is to really convert all the transcendental functions such as the sine and cosine put back into the, of the algebra, right? So it's going to make it into the exponential form. And here, yes, this would have been a nonsense for the real number, right? Because cosine is usually bounded by plus minus 1, but we are letting the z to be complex number. And yes, let's see how we can do it. So here, it's given, but you should know how to prove it. So cosine can be put into the sum of complex and conjugate divided by 2. Why? Because you know the sum and then the conjugate will be, what is it? Twice of the real part. And you know, if you let z to be e to the power by theta, you know the real part of the z is simply just cosine theta. So that's where we got that form from. Right? So, and then therefore, if you want to solve the trigonometry using the algebra, right, like the polynomials, that's the great form. You're going to put it into the exponential function, okay? It's largely to associate with the hyperbolic function if you're interested in it. It's very examinable and has been appeared many times already for paper 3. But anyways, let's have a look. So now I can put it into, what is it? E to the power of iz plus e to the power of negative iz over 2. You know, forget about the trigonometry because it was causing confusion. For me, it was a nonsense if it wasn't a real number. But now we're converting to the complex number. Let's see how it would do with this exponential form, the Euler form. So that's lovely because I can multiply by 2 on both sides to make the right-hand side to be 4. And I don't like working with the, what is it, the negative exponent. I don't like it. So what you want to do is multiply by the exponent here. Let's multiply by e to the power of iz, the reciprocal. And then you realize that it's going to be the perfect square on the first one. So it's going to be e to the power of 2 iz. You know what? Let me just put it as a e to the power of iz perfect square minus 4 e to the power of iz plus 1 is equal to 0. So that's lovely. And yes, it is, apart from the complex number, the one that is very familiar here is that it's going to be a quadratic equation, isn't it? So if I make substitution here, what you get there, my friend, it's going to be t squared minus 4t plus 1 is equal to 0. Then I can use the quadratic formula, isn't it? So if it's even coefficient, please try to use the, the reduced version. So 2 plus minus, 3. Then it was e to the power of iz, voila. And then both of them are possible because 2 plus root 3 to minus root 3, both of them are positive. It's okay for the exponential function. So that's great. Then I'm going to, put it into logarithmic form. So iz is going to be ln 2 plus minus root 3. Oh la la. That is within the domain of a logarithmic function. That's great. So that is 1 over I ln 2 plus minus root 3 is going to be a solution for this hideous cosine being 2. So the funny thing is happening in the complex number a lot, then I think it's a great discussion to make for your internal assessment or extended essay. Why funny things happen in the complex number? Why sum of integers infinite many terms will yield into negative 1 over 12? What does that mean? It is possible in complex numbers. So, if you're interested in with this example, have a look. It's a very nice, area to dive in. Oh yes, so yes, for the exponential form, for the Euler form, what's very often is to use those type of quadratical polynomial equation or in the geometric series, okay? And because, if you look at this geometric series, the common ratio is 1 over 3 e to the power of theta. And for the condition for the convergence, I want to have a look at the absolute value. But as you know, if you put an absolute value on a complex number, that's just the, the modulus. And I'm lucky to have just modulus being described well in the front, which is just the 1/3. Hence this less than 1. This means the S infinite will converge. So I'm very happy. This will converge. So what I can do here, my friend, is simply use the formula. So let's just simply use the formula. So what I'm going to do here, my friend, is that the S infinite is the first term over 1 minus r, isn't it? So very popular with the exponential form for the complex number. That's going to be 1 over 1 minus 1 over 3 e to the power of theta. I'm very happy. And here, I don't like working with the fraction. So, maybe I will multiply top and bottom by 3. So that's going to give me 3 over 3 minus e to the power of theta. And I don't like working with the complex number in the bottom either. So what you want to do is to multiply by the conjugate. But please don't forget, do not simply change this coefficient to be positive, all right? That's only applicable for the Cartesian form. We're talking the complex number. Remember, z plus minus omega conjugate is simply z conjugate plus minus omega conjugate. So for this one, you have to just remember the conjugate of a 3 and exponential form. For the real part, conjugate doesn't do anything. So it's going to be simply 3. However, for the Euler form, what is going to be that different sign is the argument, like the polar form. So it's going to be minus, is preserved, but e to the power of negative I theta for the argument, my friend, is going to be the conjugate. I'm going to multiply the same thing in the numerator as well. So let's expand. Let us expand. So that's going to be what, my friend? It's going to be 3. 3 minus e to the power of negative I theta, right? Over. And let's try to distribute the numerator. It's going to be, 9, and then minus 3, complex and its conjugate sum, and then the product of complex and conjugate, But then you realize if it's a product with the e to the power I theta and then negative I theta, that's just e to the power 0, so it becomes 1. So now I have on the denominator, that's going to be 10 minus, so if here for the sum of a complex conjugate, that's twice the real part, that's a 2 cosine theta. And I'm multiplying by the negative 3, so that's going to be minus 6 cosine 2 theta. And then in the numerator, you can just easily expand, so that's not a problem. However, I want you to remember, my friend, that if I have an exponential form, if I have a complex number, at the end of the day, what you really want to grind is to separate between very good. I really want to separate between the real and imaginary part. So that's going to be, what is it? I'm going to change that into cosine theta minus I sine theta is what you want to do. So then I'm going to compare between the real and imaginary part, isn't it? So the real part here is going to be 9. And here the cosine was the real part, multiplied by the negative 3 cosine theta over the denominator. No problem. Minus 3 times negative I will give you the positive I 3 sine theta over the denominator. So that's great. So that will be the, the simplest form of this modulus argument form. Okay. And then here's the thing. I really want you to realize, my friend, in the midst, during the computation with the complex number, somewhat the question always leads into simplify the value for the cosine or sine. It's very common to ask you to evaluate for some hideous form of a cosine or very bizarre expression of a sine like this. But that's really just to ask you to see whether you can apply the complex number to compare with what? Very good. Real part or imaginary part. And here, my friend, what we're doing right now is what? Working with the imaginary part. We are working with the imaginary part because it's just involved with the sign, and that's your job to find out. This is the deductive thinking. So here's the thing. As you can see, I had some complex number, and somehow randomly they ask you something with the infinite series of a sign. But then you realize if the complex number is always associated with the imaginary part if it's something with the sign. So I'm going to put the imaginary part there, my friend. The imaginary part of that geometric series will be what? The 1 is not an imaginary part, so I'll disregard. And for that one, it's going to be 1/3 sine theta. For that one, it's going to be 1/9 sine 2 theta. And it becomes an infinite series. Will be equivalent to the imaginary part that we already found from the infinite series. Infinite geometric series formula, which was 3 sine theta. So that's going to be equal to the imaginary part from the limit that we found from the previous part. So that's going to be 3 sine theta over 10 minus 6 cosine theta. So that is great, but it doesn't look exactly the same. How would you make it exactly the same with the answer? Very good. I will simply multiply by 3. That's what you do. Okay? So then you get to the result that you wanted to have. So yes, 3 things to mention here. So yes, all of them are very, very typical to work with the somewhat series, with the geometric series or other type of a series. Please find the pattern. And number 2, yes, while use the formula, you might have to multiply with the conjugate. It's not the negative e, but it's just the argument. And number 3, please be willing to separate the real and imaginary part for whatever the form of a complex number. And if the question asks you about the cosine, that's really to derive the real part from your existing answer. If it's something with the sign, that's really to work with the imaginary part. Okay? But yeah, it's gonna be the same thing here. I'm sure you can do the same thing. Yeah, but as you can see, what do you think we're gonna do here? Yes, whatever the formula that we have done, we found the S infinite limit. It's to compare which part? You tell me. Very good. It is really to compare with the real part. That, my friend, is how we're gonna work. Okay? But yeah, that really summarized all the form that I wanted to briefly go over. Cartesian, a lot of algebra, but very likely to just work with the simultaneous equation between the real part, imaginary part, or the fraction form, the 1 over complex number. And then you gotta be able to convert that quickly and use the algebra. But more emphasis, I think the most emphasis on the form of a complex number must lie in the modulus argument form, because this is straight up revision with the trigonometry. Whether you remember Pythagorean identity, double angle identity, half angle identity, triple angle identity, compound angle, sum to product, to name a few. Okay, so very important for you to revise that. And the third one, as you can see, is the Euler form. It's not the most popular, but it's very exciting algebra with the geometric series. Or as you have seen, some bizarre expression of a cosine z being 2 in complex number would have solution in the logarithmic form. So as you can see, everything is really intertwined, isn't it? Like the polynomial, exponential, even trigonometry and the logarithmic, they are really all put together. And then those connections can be really well described with the use of a complex number. Why am I saying that? Because it's a nice comment to make to conclude this video to give you insight for your potential internal assessment. So please dive in further with the complex number application, and maybe if you're interested in, you can also use with the calculus, and hence like swim through a bit with the ocean of the Riemann sum if you have interested in math for the either internal assessment or extended essay. But yeah, that's pretty much it with some it's essential problem, I think, for the complex form. Now I'm going to move into the complex number application. I will see you then. Hello friends, let's have a look at the complex number part 2, which involves a lot of applications, right? So 3 applications in the complex number that you have to keep in mind. The De Moivre's theorem, roots of unity, and fundamental theorem of algebra. So let's have a look what we can do and what sort of applications we're going to have, right? So, we are going to use DMT every time we see the form of what? Z, converting in Z to the power of n. Whenever you put into the higher power, we're going to use the DMT. Okay, so for the use of DMT, it's very important for you to be able to convert into the polar form quickly. So when I see things like this, for me, I would try to convert into the cis form first. So the numerator is going to be cis negative theta over the denominator. Please remember, I have a sine in the real part and cosine in the imaginary part. We don't like it. Please remember the real part must be expressed in terms of a cosine. So what we want here is the realization that I'm going to use the complementary angle, the cofunction identity. So that's going to be cosine pi over 2 minus theta, vice versa, right? So I can do the same thing for the cosine. So in the denominator, I know it's going to be cis pi over 2 minus theta to the power of 5 is what I've got, right? That's lovely. So here, what I want to do is simplify with your operation first. So top and bottom, when you have a quotient, you divide. So you subtract the argument, don't you? So it's going to be cis, what is it? Negative theta minus pi over 2 plus theta is what I've got, right? So that's raised to the power of 5, isn't it? So then I know I'm going to simplify the first in the denominator, boom, 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 simply negative pi over 2. So I'm going to have used DMT, multiplying the power in the argument. So it's going to be cis negative 5 pi over 2. And yes, it should be in your blood already to know this form already. This is either positive I or negative I. What do you think? It should be negative I, isn't it? Because it's cis, what is it? Negative 2 pi minus pi over 2. So it's equivalent to cis negative pi over 2. So I know on the argon diagram, I'm going to send it to the one below, so it's going to be negative I. So that's it. So it's going to be negative I. Okay, so for DMT, we use DMT right away. Even though the question didn't ask me to use the DMT, I'm going to simplify this into the cis and then use the power 5 into the argument is what we would do. Okay, let's move on to the next problem. So here, it's a very lovely problem here. I got the Cartesian, so they asked me to find it in who? A modulus argument form first, so let's try to use it. So, it should be very straightforward that we are able to see that this is going to be 2 cis, and what is going to be the argument? Tangent theta is root 3 over 1, so one of the special angles is going to be pi over 3, and I'm going to put it into the power of m, right? So that is a great, so that's going to be 2 to the power of m cis, what is it? M pi over 3. So that is a great. And then for the second form, what are we going to do? So that's going to be, what is it? The polar form here is going to be square root of 2 cis. And then boom, boom, I put it into the fourth quadrant. So that's going to be negative pi over 4. To the power of n is lovely. So I know that is going to be 2 to the power of n over 2 cis. And I have a negative n pi over 4 is what I've got, right? So that is my modulus argument form of each of them using the DMT. I want you to realize I put that power into the multiple of the argument. So that is a great. Hence, find the smallest positive integer m(n). That is a great. So what I'm going to do is to use a complex equality. But for the polar form, you should pay more attention to who? The argument. So, is it correct for me to say that the cis theta equal to cis phi implies the theta is equal to phi? Can I say that? No, you cannot say that, because if, for example, if I have a cis pi over 6 and cis 13 pi over 6 is the same thing because it's in the first quadrant, but I know that the argument wouldn't be the same. So you always have to add the period, which is going to be 2k pi, where k is an integer. So if I'm using the complex equality for the polar form, you've been working with the complex equality with the Cartesian form, comparing the real and imaginary part. But for this one, what I want to do is to work with the modulus and arguments, all right? So they should have the same equal modulus. I'm going to let that part to be the same as that. So I know in order for this exponent to be the same, I'm going to have m is equal to n over 2. That is great. And for the argument, I need to think about what the period, the 2k pi, it's gonna be the same if you just rotate by 1 or 2 rounds. So I'm gonna let this argument, for example, z1 to be who? M pi over 3. That argument should be the same as the argument of the second one, which is the negative n pi over 4 plus what? The period 2k pi. Is what I've got, right? So that is great. So then I'm going to get rid of the pi. So just to simplify, isn't it? So, and then I need to then try to find the the multiple of k to make this as at least positive. And thankfully, I can make substitution from the identity that I can get from the modulus. So I'm gonna put that in. M is equal to n over 2. So that on the left hand side, if I replace with the coefficient of 1/3, it's n over 6. That is a great. Is equal to negative n over 4 is plus 2k, where k is integer. So maybe I will shift that to the other side. Then what do I have? It's going to be n over 6 plus n over 4. That's 12, and 2, 3, 5n. That is great. Should be even number, right? So then I know that the, for example, if I want the k to be, for example, 1, right? Let's say k is 1. If k is 1, then this is going to come out as a 2, isn't it? It's going to come out as a 2. However, that's not a good choice, because that makes the n to be what, my friend? You're absolutely right. That makes the n to be 12 over 5 times 2, so 24 over 5. I'm letting that n to be such number, but I know that does not belong to the natural number. I need to make the n and m to be least positive integers, right? So I know that the k shouldn't be 1. So let's go, what k then should I do? Well, if I rearrange this 12 a bit here, then I get the, 5n is equal to what? 24k. Okay, so, for n to be integer number, then I want the 24 to be also multiple of 5. So then I should let k to be what? 5, for example. So that becomes 120. So that makes the n to be 24. Right, so that is great, because if n is a 24, n must be 12. So those are the number positive integer that will make this complex equality the same. So what I want you to do is, this is an interesting complex equality, because I'm not just working on the real and imaginary part of the Cartesian, but instead I'm comparing between the modulus and argument. And when you make the equality for the argument, you shouldn't forget that it needs to be counted with this even pi. Even multiple pi, because even pi, because of the period of the sine and cosine. Okay, so if the n was a 24, m will be 12 should be the answer. Okay, right. Let's move on to the next question here. Oh wow! So yes, we're gonna see a lot of lower to higher or higher to lower identity with the DMT. So for the DMT, you should really only consider 2 applications: higher to lower, lower to higher. Okay, so lower to higher, we often use it for solving trig equations. So let me quickly show you. So it says, find the expression of the multiple of 5. We already know the double angle, triple angle, and a formula, right? But now I want to prove the the multiple of 5. And yes, the common thing that we do is the use of the the compound angle for trigonometry. But for the complex with the DMT and binomial expansion, you can prove the n multiple trick, which then can be extended to something called the Chebyshev polynomial. So if you are interested in with the complex number and see the interesting view of the trigonometry, you can have a look at that as an IA topic. But let me quickly give you a preview of this. So what we want to do is to work with the lower to higher. So if you want to do that, what I would suggest is this. In the complex number, suddenly out of blue, they ask you either to work with the cosine or sine. That means you really have to work with the real part or imaginary part. So I'm looking at the sine. What part do you think I'm going to be working on? Very good. I'm going to be working with the imaginary part. So I'm going to let cis theta to be cosine theta plus I sine theta. That is great. And what I want to do here, because now I see the multiple of 5, even though the question didn't tell me, I am going to. So this is called a deductive thinking. This is the will of deductive thinking. I'm going to put into the power of 5. Right, that is great. And I want you to realize, well, if I raise the natural integer power, I know I can use the DMT. So simply this is going to be cosine 5 theta plus I sine 5 theta. But as you remember, I got the two terms and it's raised to the power of 5. I can use the binomial expansion. So let me try to expand this also binomially, right? So it's going to be sigma k is equal to 0 to 5. 5 choose k, and who's going to be my a? Is going to be cosine theta to the power of 5 minus k, I to the power of k, sine to the power of k, right? That is great. And I don't need to expand this entirely. We're going to have 6 terms if you expand everything here, but then I'm only interested in working with the sine, right? That means an imaginary part. So I'm going to compare, even though the expansion method was different, the DMT versus the binomial expansion, the real part and imaginary part respectively must be equal. Right, that's the complex equality. So that's beautiful. So I know I'm going to work with the imaginary part. So what index of that sigma am I interested in? Only the odd number. So I want to let then k to be, 1, 3, 5. That's it. All right, so I'm going to compare with the imaginary part. So let's do so. The imaginary part from the DMT is already sine 5 theta. And I'm going to let then k to be 1, 3, 5. Why? Because that will make the I remaining. If you put it into the even power, such as a 0 to 4, it becomes alternating real number. I don't want that. I just want to associate with this sign. So let's then plug it in. So if I did, my friend, it's going to be 5 choose 1. Oh la la. I'm going to factorize by I. 5 choose 1 sine theta minus 5 choose 3 sine cubic. Then the 5 choose 5, that's going to, oh sorry, I shouldn't forget what my friend, the cosine. Sorry about that. Let me just move it around. If I chose the index k1, then I'm going to have a cosine for degree 4, power 4. And then here I should have cosine square. Right, that is great. So if I let to be 5, that becomes just disappear. 5 choose 5, and sine to the power of 5 is what I've got, right? That is lovely. And that sine thing will be equivalent to this imaginary part here, okay? Oops. But obviously, you know, it's subject to factor simplification further because you see that I've got the cosine 4 and cosine square, right? You can leave it like that, but the question might ask you to actually simplify just in terms of sine. If you want things just in terms of sine, what can you do? You can use the Pythagorean identity, right? You can let this to be, 1 minus sine square square. And you can let that to be just a 1 minus sine square. And you just have to use substitution to expand them. And then what are you going to make this equivalent to? The imaginary part by the DMT. So that should be equivalent to I sine 5 theta is what I've got. Okay, so that is how we can approach this. So if you want the lower to higher power, if you want the lower to higher power, what you're going to do is to use the DMT, and then compare with the binomial expansion, depending on the real part or imaginary part. That's it. So lower to higher power, what do we do? Compare between the DMT expansion and then the binomial expansion. Right, so that will be the lower to higher. So very common practice. We're going to see over and over those multiple applications, and let's dig in more. But we also have application the reverse way. Now I have a higher to lower, and this is commonly used for integration later on. Right, it's going to be mixed with the topic 5, because you know actually the integral of cosine 5 is quite trivial, so I'm not worried. But, you know, for example, integral of cosine degree 4, that's a bit more challenging. And that application of a complex number can be used well here. So for this one, what I want you to be able to memorize and prove is the following identity. In complex number with the DMT, very popular identity is given as the following. If I let z to be cis theta, then z to the power of n plus 1 over z to the power of n is 2 cosine n theta. I do strongly encourage you to be able to prove this, and because in the exam question, it's a very popular to ask. Okay, it's a very popular. And now I want to let this to be minus. Then it's gonna be 2i sine n theta. This is gonna be the imaginary part, because you know you realize that this is complex and complex conjugate, and as you know, the sum of complex conjugate is just twice the real part, and that's how you can prove it. And I'm going to use that identity to lower the power from higher to lower, things like this. And then let me quickly show you that, right? So what we are going to do, my friend, is to use the first identity here, because that's the something with the cosine. If you are converting from the higher power of a sine, you're going to use the second one, my friend, okay? So let me quickly then perform the identity here. First, I'm going to use that one, and I let that to be n equal to 1. Then what do you have? You have a complex number and its conjugate being the same as what? Twice over the cosine theta in this case, because I let the n to be 1. Now I'm going to put into the power of who? Very good. Voila, I'm going to put into the power of 5, my friend. Okay, on the left-hand side, what are we going to do? I'm going to expand it binomially, right? So that's going to be 5 choose 0. What do we have? Z 5. 5 choose 1, z, 4, 1, so it's going to be cubic, don't you think? And then 5 choose 2, it's going to be 2, 3, it's going to be, 3, 2, so it's going to be z 1. 5 choose 3, z negative 1, so, let me just put that as a 1 over z. 5 choose 4, 1 over z cubic. 5 choose 5. 1 over z5 is what I've got, right? And then, yes, B Gauss, right? We love working things symmetrically, right? That's the Gauss method, isn't it? So here, what we want to do is to realize also from the binomial coefficient, n choose r, my friend, is the same as n choose n minus r, isn't it? So I'm going to let that to be the same. 5 choose 0 is the same as 5 choose 5, so I can actually factorize them together. So if I then combine them together, I have a z to the power 5 plus 1 over z to the power 5, and 5 choose 1 is the same as 5 choose 4, so I can factorize that together. That's going to be 5 z cubic plus 1 over z cubic. And then what is it? 5 choose 2 is 5 choose 5 choose 3, which is 5 4 divided by 2, so it gives you 10. So 10 z plus 1 over z is what I have, right? That is great. Why have I done this? Why have I factorized in a way? Because we want to use the identity we discussed already. So that one is going to be replaced as what? The first one is going to be 2 cosine 5 theta, right? So I can actually describe as just the real part. And for the second one, that's going to be 5 times 2 times cosine 3 theta plus 10 times 2 times cosine theta. That's lovely, because now it's all in the power of 1, isn't it? So that's great. So, I just have to simplify the coefficients. So let me quickly do that. So I'm going to select this and then paste it, my friend. Whee! So I'm going to let just that coefficient to be just 10 and 20. That's it. So I've got the 10. Oops. I got the 10 and I got the 20. Right? So that is equivalent to who? The power of 5 on the right-hand side. So that was, what is it? 2 to the power of 5. So that's a 32 cosine 5 degree power 5 theta. So that is a great. And I wanted to just let the coefficient to be 1. So what I'm going to do is to divide both sides by 32. I have therefore cosine 5 is equal to, if I rearrange, it's going to be 1 over 16 cosine 5 theta plus, what is it? 5 over 16 cosine 3 theta plus 1 over 16 cosine theta. So obviously you can then factorize with the common factor of 1 over 16 to induce those coefficients. So A is going to be 1, 5, and so I'm going to divide this by 32, isn't it? So that was 10 over. So this is going to be 10, right? And that is going to be 5, and that's going to be 1. right? Yeah, that's correct. So those are my coefficients. And I want you to realize this actually helps. This helps a lot to integrate, isn't it? Because now if I have to integrate that, I don't have to worry about any substitution because those are linear form, right? So, for example, the first time if you integrate, what do you get? It's going to be, 1 over 16 is just a common coefficient, so that's great. For that one, it's going to be 1 over 5 sine 5 theta, plus that's going to be, 5 over 3 sine 3 theta, and that's going to be 10 sine theta, right? So that's how we can factorize things around. So that is great, okay? So yeah, that's what we have. So higher to lower uses this following identity. The sum and conjugate is twice the real part. You let n to be 1 first, and depending on the power you want to do, you perform the binomial expansion. And you got to compare those z plus 1 over z and then factorize them together to use the identity again. Right? So we're going to see this practice over and over, but it's one of the very, very popular questions to ask during the test. Okay? Sure, this is a very nice problem also, why am I calling this also a complex number form? Because for this one, what you can do here is to realize tangent 3 theta to be sine 3 theta over cosine 3 theta. And, good for you if you already know the triple angle formula. But in this exam, they ask you to use a complex number to derive it. And how are we going to use the complex number to derive it? We are going to let this to be, cis theta. So I want you to realize, would this be lower to higher or higher to lower? You're absolutely right. This is going to be lower to higher because I want something over 3 theta. It's going to be triple angle. So what you can do is to put it into cis theta to the power of 3. And I'm going to expand this first, but by the DMT, that's cosine 3 theta plus I sine 3 theta. That is great. But what am I going to also compare this with? You're absolutely right. I'm going to let this to be by the binomial expansion, right? So it's going to be sigma k is equal to 0 to 3. 3 choose k. Cosine theta to the power of 3 minus k times I to the power of k sine k. So that is great. And what am I going to do? Compare with the real imaginary part, then boom, you can derive the triple angle formula. And let me quickly show you how it's going to look like. So we're going to use that, right? So that's what I've been talking about. So I'm going to select this. Ooh, nice. Maybe not nice. I'm gonna select that and minimize it. Oh, that's great. And then use the formula. So if I use the sine over cosine, if I already tell you the triple angle over the sine and cosine using the complex number, the result is going to look like the following. So tangent 3 theta. Now use of the triple angle from the complex number. It was a 3 sine theta minus 4 sine cubic theta over the triple angle of the cosine from the complex number. It's going to look like 4 cosine cubic theta minus 3 cosine theta. So that is great, okay? But of course, the aim here was to show everything in terms of tangent. And this is a very, very common dilemma. You want to express everything in terms of only tangent, and I got a bunch of sine and cosine. And what we can do is we can get the idea from the double angle of tangent. So instead of working with the triple, I want you to try with what? The double angle of tangent. You already know tangent 2 theta will be sine 2 theta over cosine 2 theta. So if I use the double angle, it's going to be 2 sine theta cosine theta over cosine square minus sine square. And can I please ask you what you had done to describe this in terms of everything in terms of tangent? You're absolutely right. What we actually did is to divide by the highest power of the cosine. So I'm going to divide everything, both top and bottom, by cosine square, which is essentially just multiplying by 1. So I'm not changing anything. But if I do that, you realize that we will just cancel out with 1 power of cosine, still bottom with the cosine. So that's going to be 2 times sine over cosine over, I'm going to divide 1 by 1. So that's going to be 1 minus tangent square. Sorry, 1 minus a sine square over cosine square, which you realize a sine over cosine is simply just a tangent, isn't it? So we have the famous double angle formula for the tangent like that. So it's going to be 2 times tangent over 1 minus tangent square theta. That's the very common double angle form that we already know of. In IB, I want you to always try to push yourself to remember the proof, because there are many show that problem before solving the equation, and this is one of them, right? We must have seen this one before from the double angle, because you would then gain the idea of being able to express everything there using what? using the only tangent. So let's have a look. So for example, for the triple angle, what do we have to do? We got a bunch of sine and cosine, but I want to get the idea of getting a tangent. So what do you want to divide top and bottom, similar to the double angle? Very good. I want to divide everything by who? Great answer. Cosine cubic, because that's the highest power at the moment. Okay. So you will get quite a few terms in terms of tangent, but you will still end up having a lot of terms with the secant square. You're going to have a lot of terms with the secant square. But that's not a problem, isn't it? Because we have what? Is it because we have the Pythagorean identity? I want you to remember secant square is 1 plus tangent square theta. So if I use a bunch of substitution, blah, 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 you are going to end up having that. So I want you to practice. I want you to try yourself if you can prove it. I gave you a lot of hint already. Derive the triple angle formula, use of the complex number, comparing between the binomial and DMT. That's number one. And then number two is what? Use it. Bunch of sine and cosine, bunch of sine and cosine. But if you want to attempt to describe everything in terms of tangent, what you typically do is to divide by the highest power of the cosine. From the double angle, we divide everything by the cosine square top and bottom. For the triple angle, I'm going to divide everything by what? Cosine cubic. And you're going to get quite a few tangent, but several times you're going to be secant square, but not a problem because I can use the Pythagorean identity to express just in terms of tangent. And you're going to end up having that. So that is great, okay? So then I want to use this formula to get the, what is it? Tangent 15 degree. So that is great. What are you going to let your theta to be? Very good. Let the theta to be 15, right? Then I'm going to get a bunch of tangent 15 here, no problem, which I don't know. I got to solve it. But on the left-hand side, if I let the theta to in the triple angle formula, that becomes tangent 45, which you already know. That's just simply 1. No problem. So that's great. I'm going to use then, so I'm going to then expand it. So if I let the tangent 15 degree, don't forget the unit, as t, then it becomes quite a nice, quite nice cubic polynomial. So that is a great. And you know, obviously, if you want to solve the equation, you know, I should know the roots. And for this type of typical polynomial with the cubic, it's very common that it's got rational root. So we can do the rational root test. So if it has a rational root, it's not a guarantee. If it has one, it must be in the following form. T must be the plus minus factor of the constant over the factor of the leading coefficient. So, you know, it's got the 1 and 1. So the only values that I'm going to typically try is just plus minus 1, isn't it? So if I let that to be the value that I'm going to plug it in, let's see what I get. I didn't write. Let's just solve it here. So you know, so now we are very happy with this polynomial. So what I want to do is to find its root. So you know, I'm gonna do the synthetic division. So 1, -3, and 1. So if I want to try with the solution t to be, for example, 1, I know that's going to fail because if I put 1, typically I can see that it wouldn't be 0. So I'm not going to bother with 1. Let's directly go with the -1, right? That is a great. So if I do the synthetic division 1, multiplying outside, that's -1, -4, 4, 1, -1, boom, I got that to be 0, right? That is a good. So it's going to be t plus 1, voila. I've got, what is it, t squared minus 4t plus 1 is equal to 0. Oh, wow, then I can do the null factor law, right? So a times b being 0 means this has to be 0 or that one has to be 0, right? But as you know, my solution is supposed to be tan t, which is a tangent 15 degree, my friend, which should be always a positive because I got the positive acute angle inside. So it must be positive. So I know that I'm not going to bother with the t equal to -1. I'm not going to bother with that. So my solution must come from this quadratic factor. All right, that's great. So, you know, I got the even coefficient. So if you got a chance with the even coefficient, please try to use a simplified version of the quadratic formula. So t is going to be 2 plus minus square root of 4 minus 1 using the reduced quadratic formula. So that is great. So it's going to be 2 plus minus root 3. That is the option for the tangent 15 degree. But I'm still not done. Why not? Because I want you to realize I got the case of a positive or negative. I have to verify whether it should be positive or negative. And for this type of a dilemma, you're going to have 1 or 2 cases that's going to ask you to verify whether you should have the the positive or its conjugate for this third form for the trigonometry. And what I would encourage you to do is check with its monotonicity. So what I mean by that is that for the tangent function, you know it is strictly increasing from 0 to pi over 2. But in this time, we're talking in degrees, so let's go with 90 degree. Right? Tangent is strictly increasing from 0 to 90 degree. That is a great. And your answer was what? Tangent 15. Right, so 15, I got the tangent 15, that's a t value. And I know then it must be less than what? For example, if I compare with the 45 degree, tangent 45 is 1. I know this value must be less than 1. But if you let the sign symbol here with the positive, that makes well above the 1, which is not going to be a good choice. So I'm going to let this to be what? To minus root 3, because tangent 15 is less than 1, right? Because of the increasing part here. Okay, so that's how we can find it. And I'm going to leave you an exercise to find the tangent 75, which is going to be very similar if you think about, because if I let theta to be 75 degree, on the left-hand side, that's a 225. And using the reference angle, I'm still going to have that as 1. So you're going to have the same polynomial. So he must be one of the solutions we found here. But obviously, tangent 75, it's still the first quadrant, so positive acute, still should come out as a positive. So I'm not going to bother with tangent theta being -1. So it must be one of the solutions for the quadratic. But I already chose the one with the negative, so I'm sure that it's going to be very likely to work with the 2 plus root 3. But to understand that, you should really check with your trigonometry. I want you to remind you again, complex number is really just straight up revision for the trigonometry and vector. So it's a very, very beautiful topic for the revision. Okay? Let's move on. Let's move on to the next question, please. Okay, so yeah, this is another form. Remember, as soon as you see that, I want you to realize that this is a 2 cosine n theta, but not only memorizing, but as you can see, we have to be able to prove it for this one. So please practice. Please show me that you are able to prove this. Okay, so that is beautiful, right? It's because now I can compare this expansion here. Let's try to expand this one. So it's going to be, what is it if I expand? So it's going to be the binomial expansion. So z cubic plus 3, z squared, z cubic plus 3, z conjugate square plus z conjugate cubic. Right, that is lovely. And what we just showed was that z plus z conjugate is the twice of the real part of the complex number, but we let the z to be cis. His real part is simply just cosine, so it's going to be 2 cosine theta. And I'm putting into the power of 3 for that part, so that's going to be 8 cosine cubic. So that is a great. Okay, then yes, as you can see, what we typically want to do is to pair them symmetrically, isn't it? So that's going to be cubic, conjugate cubic, so z cubic plus z conjugate cubic. So that is a great. And for the second and third part, that's going to be 3 z times z conjugate. If I factorize that, that's going to be z plus z conjugate. That is lovely. And what we can do is we can use the identity over there, which was then what? It's going to be 2 cosine how much theta? What can you say? What's the end value here? Very good. That's going to be 3 theta, right? That's great. And the product of a complex and conjugate will be simply just 1 in this time, right? So because it's a cis 0, that's 1. So I have a 3 times, well, sum of complex and conjugate, that's going to be twice of the real part. Wow, wunderbar. So then we have that number, that expression, same as the 8 cosine cubic. So then I know cosine 3 theta is going to, we can then derive the, the triple angle formula, isn't it? So if I do the rearrangement, blah, 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 you end up having, I'm going to divide by 2 on both sides, that becomes a 4. So then I have cosine 3 theta is going to be 4 cosine cubic theta minus 3 cosine theta. So that is great, right? That's how we can prove it. And of course, whenever we have these proof questions, what you're going to end up having is to use it, right? So we prove this, and then let's use it for the last question. This is a great question. So every time you prove something, I really want you to use your deductive thinking to plug it in and use it. So what I mean by that is 4 cosine cubic minus 3 cosine theta. I see it in the form right there. So we should use it. So I'm going to use it as what? A cosine 3 theta. So that's lovely. However, I'm doing the minus 2 cosine squared theta plus 1. That's the double angle of a cosine, isn't it? So I'm going to have minus cosine 2 theta is equal to 0. Okay, that's lovely. So if I do the rearrangement, I have cosine 3 theta is equal to cosine 2 theta. And I do not want you to make the common mistake. I don't want you to just let this to be 3 theta being 2 theta only. Because remember, it may be one of the solutions. You're absolutely right. But it's a trigonometric function. Trigonometric function, depending on the intersection, it can have more than one solution. So I cannot let the range being the same implies the domain the same for this periodic function. It may be if it was restricted for a certain interval to make it as a one-to-one function, but it's not in this time if it's going from 0 to pi. So what I want you to do is that for the trigonometric equation, especially when you have a sum or a difference, you can put them together using the factor formula. So every time I see the difference of a cosine like that, I want you to please remember if I have a cosine, for example, A minus cosine B, according to the sum to product formula, this is the same as who? Negative 2 sine A minus B over 2 sine A plus B over 2. Voila. So please memorize it, okay, that you are able to come up with this. So then for this equation here, I don't actually rearrange because I want to put them in the multiplication. If I put them in the multiplication, what do you get, my friend? This is going to be 2 cosine, oh la la, theta over 2, and then cosine, what is it, my friend? Sorry, negative. 5 theta over 2, right? And that is equal to 0. Oh la la, that's great. Why? Because when it was a sum or difference, you feel that to be 0. There are many, many cases I can think. But if it's in the product, I can use the null factor law. What does that mean? Either the first term has to be 0 or the second term, isn't it? So that's great. So if I have, what is it? The domain from 0 to pi, then theta over 2 must be bounded by from 0 to pi over 2. For that one, this is not possible to be 0, isn't it? Because I need that to be pi over 2, but it's open interval. It does not involve, so I can't use that equation. Okay, that's interesting. But if I look at the second one, so 5 over 2 theta now belongs to from where? From 0 to 5 pi over 2. Okay, that's great. And for that one, I can actually have quite a few answers. So I can let 5 theta over 2 to be what? Well, so cosine is 0. That's a pi over 2 plus integer pi. So I got to let this to be pi over 2. Or what can you do? 3 pi over 2 is fine. Can I let this to be 5 pi over 2? No, we cannot because that's open interval. Sorry, it was open interval. So I cannot contain that, right? So that is a great. So from this, if I do the rearrangement, then you let this to be, what is it? Pi over 5 or 3 pi over 5 will be the exact solution for this trigonometric equation, okay? So make sure if we come down to the sum or difference of the trigonometric function with the same coefficient, my friend, then I can do the sum to product formula, okay? But if you got the different coefficient with the same period, we use something else. You know, we use the sum of a sine and cosine with the simultaneous equation of a compound angle. We can have a look at that in the topic 3. But for this one, we had to use the sum to product formula, okay? That's great. But yeah, moreover, what is it? This is also lower to what? Higher. Okay, there you go. Right, so there's a lovely question here. Many, many applications with the DMT and then the trigonometry. So please remind yourself. Before we start with this practice, let me take a 5, okay? And now I'll be back. See you in a bit. All right, let's have a look at the next part of the second part, the part 2 of a complex number using the applications. So let's get to it. So for this one, you know, what we had to do was to use the sine 5 theta. Okay, you know, if you ask me why, how do I know it's a sine 5 theta? Well, exam question was like a build-up question. They ask you to find the sine 5 theta, right? So, and as you can see, this is going to be the typical form with the lower to higher using the comparison between the DMT and the binomial expansion, right? So for that one, you would have done then the imaginary part of who? Sure, this would have been the imaginary part of the so cosine theta plus I sine theta to the power of what? 5, right? So using the by DMT, right? So that would have been the form that we wanted to do. And then you would have then have a sine, let's say 5 theta is I don't quite remember, but it was, I think, sorry, I don't remember. It was like a 16 sine. Well, you know what? Let's do it together. This is a revision video, so why not? Let's do this together. So I'm gonna let this to be, what is it, the degree 5, so it's going to be sigma k is equal to 0 to 5, so 5 choose k, and then cosine theta to the power 5 minus k, I to the power of k, sine k theta is what I have, right? So that is a great. So for that one, now I have, what is it? It's going to be, well, for that one, I want to get the imaginary part only. So that's going to give me, what is it? It's going to give me the, let's expand. So it's going to be only with the k being odd, right? Because I want to get the imaginary part, yes? So let's then dig in. So it's going to be 5 choose 1 cosine 4제곱 sine theta 빼기 하다다다다. Well, you know, obviously it's going to be common multiple by, and then 5 choose 3 cosine squared sine cubic theta. Okay, and then 더하기 sine 5 is what I have, right? So that's great. So let's use the coefficient. 5 choose 1 is a 5, 5 choose 3 is a 10, so 5, 10. So that's great, isn't it? Okay, so that's lovely. So for that one, it's going to be the sine, what is it, 5 theta is equal to, I've got this following form, but you know, I am able to express this in terms of just sine because I can use the Pythagorean identity. So that is going to be same as it's a cosine squared, and using the Pythagorean identity, that's going to be 1 minus sine squared. So that I'm going to have a, you know, of that one, it's going to be put it as a 1 minus 2 sine squared plus sine to the power 4. That's great. Then for that one, I'm going to use the Pythagorean identity 1 minus sine squared, right? So that is a great. Okay, so and imagine that I'm expanding this, so it's going to be multiple by, and if I expand it, you know, I'm going to then put it into the like term, so degree 5 here, and that's the, so that one can be put together with who? 5 minus positive square sine cubic, so that's also sine degree 5, so sine degree 5, I'm going to factorize that by who? 1, and then for that one, plus 10, that is great, plus 5, okay? That's great. So then the next term that I can compare with is the sine cubic. So if I did, it's going to be sine cubic, minus 10, positive 10. That is a great. And for the sine theta with the cubic, minus 10. Sorry, is it? Yes, it's minus 10. Oh, does it become 0? Oh, sorry, that's negative 10. So that's a negative 10, 10. So plus 10 here, put into the minus, it's actually going to be negative 20. Oh, okay, that is great. That's lovely. So then let's have a look at the sine theta. So that's a 5. That's it. I got the plus 5 sine theta only. So I expanded it and put them in the like term, right? So that's great. So here it's going to be, what is it? I. And for that one, that's going to be 16 sine 5 theta. That's great. Minus 20 sine cubic theta plus 5 sine theta is what I've got, right? So that's great. So for that one, should be the same thing as the imaginary part of the DMT. So I'm gonna let that to be the same as the imaginary part using the DMT. So that is a great. And now I'm gonna let that to be who? I'm gonna let the theta now is the 2 pi over 5. I want to find theta to be 2 pi over 5, right? So that's great. So let's do that. So if I substitute in on the left-hand side, that's a sine 2 pi, which becomes a 0. So I got the 0 on the left-hand side, all right? And then on the right-hand side, I don't have any. Okay, so I'm gonna let, what is it? Sine 2 pi over 5 to be just s. I don't know what that value is. It's my job to find it. So I got the degree 5 polynomial using this substitution. But I want you to realize I can reduce this further. How can I reduce this further? Well, first of all, it can never be 0 because it's not an integer pi. If you want to let the sign to be 0, you got to make it as an integer pi. So I'm going to let this to be 0. And then what I'm going to do is divide both sides by the sign because it's never 0 for the 2 pi over 5. And if you divide, you can lower the degree, it's better for us to work with. So if I then divide by the sign on each side, and I'm going to duplicate this, then the power becomes 4, 2, 0. So that's great. So then I have, what is it? Then I have 4, 2, and then the constant, right? So that's great. Why is it great? Because now I realize I can actually solve it using the quadratic equation, using the another substitution, isn't it? So if I use another substitution here, my friend, what you realize, let me just make more space, is that if I let the s squared to be t, then that equation becomes 16t squared minus 20t plus 5 is equal to 0. That's lovely. So if I use the, what is it, the reduced version of the quadratic formula, because I got the even coefficient, t is going to be 10 plus minus square root of 100 minus 80 over 16. So that is a great, so I've got the 10 plus minus square root of 20 over 16, and that was a sine squared 2 pi over 5. That is great, right? So let's then simplify further, right? If you simplify this further, what I realize is that it's going to be 5, 5, 8. So I'm going to have 5, 5, 8. That's the simplified version. So I have sine of 2 pi over 5 will be plus minus square root of what? The inside of the square root. So that's going to be boom, is what I've got. And what I want you to realize is that I got the positive minus, positive minus, right? So that's positive, negative, positive, negative. And I have to verify which one is going to be, in fact, the actual solution, because it's a function, so it must be unique. I must choose the according value of radian, but I want you to realize 2 pi over 5, which was a 72 degree, is a positive acute angle. So it is inevitable. It must require the outside to be positive. So that's a lovely choice. I know that I'm going to, work with the positive outside, right? So that is great. So I'm going to work with the positive outside. However, I need to verify whether it's going to be positive, negative inside. And I want you to realize every time you, like I said before, we actually took a look at this similar example before, haven't we? Because every time you have to sort of you choose the positive, negative in series form with the trigonometry, what you often do is to compare with the monotonicity of a function. So you know a sine function is strictly increasing from 0 to pi over 2. All right, and this is it's a 72 degree, and the special angle that is very close to this is going to be 60 degree, which I can compare with the. So if I let this be 2 pi over 5, the one that is slightly less is going to be pi over 3. We know that from the increasing property of a function from 0 to pi over 2. And then you know the sine pi over 3 is root 3 over 2. And if you compare this, who should be bigger? Who should be bigger? The left-hand side must be bigger. We know that, right? But if you let the in between the negative, and if you do a bit of algebra, you end up realizing it wouldn't be bigger than root 3 over 2, which is supposed to be the given condition. So contradiction arises. So you have to verify after solving the equation which one is going to be positive or negative. Okay, that is a must do. So then we verify the outside being positive from the fact that the 2 pi over 3 is an acute angle triangle. Acute angle. And then the second thing, the one that we did, is to compare with the given angle, special angle, given angle, we're using the monotonicity. So then we realize, this must be positive, square root of 5, positive with 5 over 8. So that's a lovely answer for this nice DMT related trigonometric value equation. And what they can then accordingly ask you is, okay, what about sine pi over 5, right? I don't want to go over all this step again, right? I don't want to. But I want you to realize if you remember I got rid of it, but sorry about that. But we had a 16, so what was it? The sine, 5 theta was that equation, right? So here we had that, right? And if you had the theta to be now pi over 5, you realize that also becomes a 0, okay? So this sine pi over 5 can be another substitution, my friend. And it's going to yield the same polynomial. So in fact, you're going to also derive the same value, right? You're going to end up having plus minus square root of plus minus over 8, whatever. But it's simple to write, so let's just do that. You're gonna have that. You're gonna have that for pi over 5 as well. But you have to verify which one is going to be positive or negative. But in fact, for this one, sure, pi over 5 still positive acute. So it's in the first quadrant, should make the sign positive. So I'm going to have a positive outside. But in between now, the positive was unique for the 72 degree, the 2 pi over 5. So for the pi over 5, which is 36 degrees, should have the minus in between, right, to make the function exist. So that's great. So that's how you can verify whether it's going to be positive, negative, outside, or in between. Let's go with the 3 pi over 5. Sine 3 pi over 5. Oh, well, you may plug it in also, but in this time now I can use the reference angle, you see? Because now this is going to be sine pi minus 2 pi over 5. I want you to realize. And from the reference angle, this sends to the second quadrant, doesn't it? So now I know that that's going to be sine 2 pi over 5. So it's actually going to be the same answer from the first one. That is lovely. Let's go with the sine 4 pi over 5. What would you do, my friend? That's going to be sine pi minus pi over 5. So that's actually going to be same as the positive and negative, right? And if you look at the sine 6 pi over 5, what would you do? Using the reference angle once again. If I use the reference angle once again, where's the eraser? Oh, sorry. If I use the sine 6 pi over 5, using the reference angle, what I realized, that's also reference angle, so sine pi plus pi over 5. I send it to which quadrant, my friend? The third quadrant, where only tangent is supposed to be positive. So I know it's going to be negative. So it's going to be negative sine pi over 5. So that's the one that's going to have minus, minus, inside, outside. It's going to be negative square root of root 5 minus root 5 over 8. So that is lovely. Okay? So that is how we can extend the value for the other reference angle. And that also was a very popular exam questions using the DMT and then the trigonometric equation. So you may also try something like this, right? So this is also another equation related to what we just have talked about. So make sure for this one, you know, what do I want? I want to have a trig equation that can make this to be 0. And then, you know, what multiple would you like to choose? You know, what multiple would you like to choose so that if you put that theta to be the 7 pi over 10, that will make it 0. Well, you know that the cosine is 0 if it's a pi over 2 plus k pi. So then I know, okay, I'm going to actually choose 5 theta, right? Because that will make the cosine to be 0, and that's a nice equation to start with. So it's actually very similar to the previous one, only the fact that I'm going to use the real part. And with this, you can also end up finding the remaining values to be like the pi over 10, 3 pi over 10, 9 pi over 10, etc., using the reference angle as well, my friend. Okay, so please help yourself to evaluate this exact value as well. You know, that they're very popular for the exam. Okay, and then yes, you know, another application for the complex number is to work with the polynomial, which is called the fundamental theorem of algebra. So let's have a look. So if I'm looking for the degree 4 polynomial using this, you realize for the degree 4 polynomial, I only have 2 real roots. So I'm gonna let this to be the leading coefficient A, and then the x minus 2, x plus 4, right? That's great. And this is a quartic, so I know if I got the quadratic, the remaining must be the quadratic as well. So your job is to find what? Those A, B, C. But I think for this problem, I think they gave you the, leading coefficient to be 1. So that's great. So, and then the passing point was, what was it? The -1, -18. -1, -18. So let's use it. So what I mean by that is, you know, they gave you the leading coefficient to be 1, so I'm going to use it. And then what you end up realizing is that I can use that, and then the y-intercept to be 0, -32. So that's great. So if you plug it in 0, my friend, I get -8. And if I put 0, that's C. And I want this to be -24. Sorry, -32. Then you realize C must be 4. So I'm happy that C must be 4. Okay? And then I got to find the B, right? So for the B, what would you do? I will use -1, -18. So if I use that, it's going to be -18 is equal to, if you plug it in 1, that's 5, -1, -5. Oops, maybe a bit weird. Sorry about that. I did the 1, but it should be -1. So I have a -3 times 81, so -3. And then if I plug -1 there, my friend, that's 1 minus b plus 4. So that's a 5 minus b. So I have a 5 minus b. That's great. And then what you end up realizing that that's a +9. So I got the 5 minus b is equal to -2. Therefore, b must be who? I might have done the computation wrong because I think the number was very clean, like 3. So let me see which part I have done wrong, my friend. Sorry about that. 9. Oh. I think that simplification was wrong, isn't it? Minus 2, 1, minus b, 5 minus b, 5 minus b. Oh, sorry, b has to be then 3, right? That's 9. So I got negative 18, sorry, negative 2 is equal to 5 minus b. B must be 7. I don't want that. I think I must have done something wrong. Let me see the passing point again. Negative 1, negative 18. Negative 1, negative 18. Oh, yeah. Where have I done wrong? Can you please point it out for me? Is there any part that I've done wrong? Minus 2, minus 4. And negative 1, negative 18. Negative 18 is equal to who? Minus 3. Oh, sorry. It should be just positive 3, isn't it? My bad. So it's going to be negative 9. So boom, boom, it becomes a positive 2. So B must be 3. Sorry about that, okay? So I'm happy. So I've got 3 and 4. Okay, I got 3 and 4. So here, 2 plus 4, 3, 4 are the values that I have to find. That's great. Sorry about that, okay? But now I got the quadratic equation here. X squared plus 3x plus 4 is equal to 0. If you check with the discriminant, that's a 9 minus 16, that's a negative, so I know I'm going to have 2 distinct complex roots. So that's what they have asked me to find. Firstly with the Cartesian form, so let's use it. So x is going to be negative 3 plus minus 2, 9 minus 16 over 2. So that's going to be negative 3 plus minus I root 7 over 2 is what I've got, okay? That's great. Now I should be able to indicate that on the Argand diagram. So I got the real and I got the imaginary axis. Okay, so that's lovely. So here, let's plug it in. Where am I going to plug it in? So the roots were 2 or negative 4. So I got the 2 here and then the negative 4 there. Okay, and the complex number were negative 3 plus minus. So just like that. I think, if you check with the modulus, I got the 9, 7 over 2, so that's the 1 over 2 square root of 9 plus 7, that's 16, 4, so the modulus is supposed to be 2, so it should have the same size like the 2 here, so it's going to look like that, isn't it? So you have to indicate on the Argand diagram. That's very lovely. And then what you had to do was to write in the Euler form. So that means you got to find the modulus argument, and I love this problem because it really asks you to use the trigonometry very well and precise definition to convert from the Cartesian to the the polar form. So let me quickly show you that. So here, by the fundamental theorem of algebra, I know for the degree 4 polynomial, I should have the 4 distinct complex roots. 2 are real, 2 are imaginary, right? 2 are complex roots. So for that one, then, for 2, I'm going to just write as a modulus, and then the argument is just 0. That's fine. And negative 4 is going to be 4 times e to the power of I. And what argument makes the e to be the Euler form to be negative? Sure, pi does. Okay, so that's great. However, for this complex roots, I want you to be very careful. We already figured out the modulus, didn't we? That was a 2. So for example, if I were to find the argument of the negative 3 over 2 plus root 7 over 2i, I already found the modulus, that's great, but I want to find the argument. And so please follow me. For me, every time you want to work with the argument, I will always try my best to indicate this briefly on the Argand diagram. I must send it to the second quadrant, all right? So and then how do you find the argument? If I let this argument to be theta, tangent theta is the imaginary part over the real part. Okay, that's great. But a very common mistake is that people make that, the theta must be arctangent, the inverse tangent of negative root 7 over 3. And that is a very, very common mistake because arctangent, my friend, is bound, his range is what? His range is from negative pi over 2. Arctangent x is from negative pi over 2 to pi over 2. So you can only find the argument either in the first or fourth quadrant, but I gotta send it to the second quadrant. So what do? I cannot use the inverse function alone. I need to think about the reference angle of a trigonometry. So I want to send to the second quadrant. So what do? For this one, I don't use the inverse tangent of the negative value. Instead, I'm going to go by pi first and then subtract by the acute angle. That would have given the tangent to be positive root 7 over 3, which is going to be just arctangent over root 7 over 3. So as you can see, that argument is certainly going to send to the second quadrant. Okay? So I cannot just simply use calculator. I cannot just use the inverse trick to find the argument. You have to think which quadrant you want to send. So for that root, I'm going to write as a negative 3 over 2 plus I root 7 over 2. It's going to have the modulus of 2, EI. And then what am I going to put? Pi minus arctangent of root 7 over 3 is what I'm going to do. So make sure you're able to find the argument using the trigonometry, but precise definition using the reference angle to send it to the second quadrant. If you ask me how do you find the other solution, well, it's conjugate. So you just have to do the negative multiple for the angle. That's pretty straightforward to find. But what I want to emphasize is that do not just use the inverse trick. Think about whether it can be in the range or not. If it's not, then you need to add the extra pi or negative pi. Okay? So a very, very nice problem. Let's move on to the next question. So yeah, we already have done that. That's fine. Oh wow, that they have explained it. So now, yeah, another very nice equation using the identity of a polynomials. Okay. So in the exam, if the fundamental theorem of algebra comes a very advanced problem, it works like this. You're gonna have a look at the polynomial that has what? This symmetric coefficient. And in fact, if you want to solve the polynomial equation, what do? We simply do the rational root test, right? We simply try to put plus minus 1 into the z and see if it's 0. But you realize none of that plus 1 or negative 1 makes this to be 0. So that's unfortunate. So we need a different approach. So what I want you to do is to use a complex number, especially the following identity. For this type of polynomial with symmetric coefficient, please remember to use the following. Z plus z power n, 1 over z power n. What was it? We have done this many, many times with the Moivre theorem. This is 2 cosine and theta. And proving question of that is very popular, so please also work yourself. And what I'm going to do is, okay, clearly z is not 0, because if you put 0, it doesn't make it 0, so I know it's not a solution. So that makes me relieved to actually just simply divide by z, okay? Well, sorry, what am I actually going to divide? Let me try to divide by the z square, okay? Let's do that. So if I did, then I'm going to have, what is it? Z square plus 3z minus 2 plus 3 over z plus 1 over z square. That is lovely. And what I'm going to do is to factorize by the first and last symmetrically, like Gauss. Right? That technique is used a lot even in competition problems. I'm going to show you. And if we pair them, it's going to have z squared plus 1 over z squared plus 3 z plus 1 over z negative 2. That is great because now I can use the formula there, right? Then it's going to be 2 cosine 2 theta plus 6 cosine theta minus 2 is simply equal to 0. So now I put it into the trigonometric expression, right? And let's try to solve it. Well, I want to solve this to be 0, but then I realize, what do you realize? That I don't like working with the double angle and theta at the same time, right? Well, first of all, let's simplify, meaning that I got the even coefficients of 1, 3, 1, isn't it? That's great. Okay, and cosine 2 theta is same as who? It's going to be 2 cosine squared theta minus 1, right? So let's plug it in. So if you plug it in, boom, I'm going to duplicate. So that's great. And then I'm going to add this. Oh, wow. And I'm going to add that. Okay? So that's great. Let's rearrange. So it's going to be, what is it? 2 cosine squared plus 3 cosine minus 2 is equal to 0. And I want to see if it's a factorizable. So let's plug it in. 1, 2, 2, 1, plus minus. Right? So that suggests cosine theta is negative 2 or 1 over 2. But for real value of theta, I know that's nonsense. Okay? So that I'm going to just stick with the cosine theta to be half. So that's lovely. For that one, I'm going to have a cosine theta to be half. That suggests the theta has to, that suggests the sine theta has to be who? Plus minus root 3 over 2 using the Pythagorean identity. That's lovely. That's great. And what's the benefit of having that? Because now you found the solution of the z. Z is a cis theta, we said, We assumed. That's why we were using that identity. And now, with this form, now I know it's going to be, what is it? 1 over 2 plus minus root 3 over 2. That's great. That is a great. And then for the fundamental theorem of algebra, what I really want you to remember is this. What I want you to remember is that if the z equal to a plus bi is a root, you know his conjugate is also a root. So if you have a root and conjugate, you have two roots. That means you got two linear factors. If you expand, you got a quadratic factor, don't you? So it's going to be z squared minus 2 real part of the z times, so you know it's going to be negative 2a. Oops, sorry, let me use the x here just to distinguish the root and the variable. X plus the modulus of z squared. I want you to always realize that it's going to be the quadratic factor if I was given a complex root. So for me, that one is going to give me what? My quadratic factor automatically will be z squared minus z plus its modulus is simply 1. Voila, I have that, my friend, as my quadratic factor for this polynomial without given root if the coefficient were symmetric. That is lovely. That is lovely. So we were using a bunch of the complex number here and its application with the trigonometry, right? Okay, so for that one then, let's see. What I can do is now, I got a quadratic vector, didn't I? I got the quadratic vector, but I got a quartic polynomial. So I got to find two more. Then what can you do? It's a factor. It's supposed to be a factor, so it must divide the polynomial. That is great. So let's see if we can divide. So I'm going to have z4, 3z cubed minus 2z squared plus 3z plus 1. And I'm going to try to divide this by the supposedly the quadratic factor that we found from the extensive use of a complex number and its identity. That is great. So let's go. So I'm going to go with z squared. Oops. Z squared minus z plus 1, right? That is a great. Let's plug it in. So I'm going to go with the z squared. So that is a great. So z4, z cubed, z squared. Let's subtract. If I did, what do I have? Cancels out 4z cubic minus 3z squared plus 3z is what I've got. That's great. And then what am I going to do? I'm going to put it as a 4z to make the coefficient the same with the degree. So it's going to be 4z cubic minus 4z squared plus 4z is what I've got. That's great. And I'm going to subtract. That's good. Boom, boom. What do I have? Z squared minus z plus 1. Then voila. I just have to let this to be positive 1. Oh, wow. That makes same thing over 0. Oh, wow. It does divide. I'm very happy. So now I can rewrite the polynomial like the following. Now I found the two quadratic factor, my friend, using the complex number and then the long division. Lovely. So now what am I going to do? So this is a factorizable with who? Z squared minus z plus 1. And then the other one will be z squared plus 4z plus 1 is equal to 0. So, by the fundamental theorem of algebra, I know I got to find the 4 distinct roots in complex number. So we already found this one. It was, 1 over 2 plus minus root 3 over 2i. And then I'm going to find another one using the quadratic formula from there. But if you check with the discriminant, that's going to be 4 minus 1. That's positive real. So it's a positive. So I know that it's going to have 2 distinct real roots. So that's great. Let's use the quadratic formula for it because obviously by inspection it's not factorizable and it's got the even coefficient. Please use the reduced form. Whenever you have a chance, it's just to reduce the time. So it's going to be negative 2 plus minus root 4 minus 1. Then I'm very happy to have these 2 real roots. You found the 2 complex roots, 2 real roots is for the answer for that polynomial. So please remember this is the applied version of the polynomial with the complex number. You got a quartic polynomial. Typically, it might have a rational root, so you can do the rational root test. And obviously for this one, if I apply plus minus 1, it did not make it 0. And the next thing to check is that I got the symmetric coefficient by the end values here. 1, 1, 3, 3, 2, negative 2. So I know that it's going to be very likely to use that identity. And I'm going to start dividing by the z squared and use the identity that we learned from the DMT. Okay, so this is a mixed version of the fundamental theorem of algebra and then the DMT. So very lovely problem. Very lovely problem. So, now you can do the same thing for the second one. Like, you look at this. This is, again, what? The symmetric coefficient. So I know I'm going to, again, divide this by z squared. And then compare the, at the far end coefficient 1 by 1. So I'm going to have 3 z squared plus 1 over z squared. And then 2, z plus 1 over z. And then plus 1 is going to be 0. So this is going to also reduce to the trigonometric equation, isn't it? With the cosine 2 theta and cosine theta, you can end up applying for the doubling of formula. So it's a 5, -1, again, symmetric, simply just divide by the z squared, apply the method that we just have discussed. Okay? Great stuff. So let's have a look at the next problem here. Oh, our favorite roots of unity. I got a lot of things to say actually, because recent AIME problem, 2023, question number 8 were involving the roots of unity. So if you're actually active IB student who were learning that, would have solved it without any problem, right? So I'm going to make another video based on that. So it's a very important stuff to remember. So every time you are having z to the power of n equal to something, but you want to find its nth root, then according to the roots of unity, I need to have n distinct roots. So I want you to always remember the formula. If I had a cis theta, what do we do? Boom, it's going to be cis, not just the 1. Please remember theta plus 2k pi over n, where k is who? From 0 to n minus 1 to make it distinct, my friend, right? That is great. Okay, so at least positive for that one. 1 is a cis is 0, isn't it? So then, z to the power 5 is cis is 0. So z, according to the formula, it's going to be cis 2k pi over 5. But I want at least positive, so that k, I need to let k to be 1. So I will let the omega to be, what is it? Cis 2 pi over 5. That's the least positive argument. That is great. Then deduce the following form. So that's sum of roots of unity. I want you to remember 2 things. Sum of roots of unity is always 0. Product of roots of unity is alternating. It's a -1 to the power of n plus 1. So I want you to remember these 2, and you should know how to prove it. There are many ways of proving this sum of roots of unity, either using the geometric series or the factorization. So let's have a look. So if you want to derive the sum of roots of unity is 0. Okay, so let's have a look. So as you can see from z to the power 5, the distinct roots you're going to get is 1 omega squared going all the way to omega to the power 4. You have 5 distinct roots from the roots of unity. Lovely stuff. And then what I realize is that, okay, I'm going to rearrange this to the other side. So z to the power 5 minus 1 is equal to 0 if z was cis, 2 power over 5. It was omega because it was a root. It was a root, wasn't it? So let me plug it in. So if I plug it in, I got omega to the power 5 minus 1 is equal to 0. But for that one, we can actually factorize further. It's going to be omega minus 1, omega 4, all the way to 1 is equal to 0. Okay? And it must be 0 because it was a root of unity. However, I need to compare that either this one is a 0 or the second part is a 0. But if you let the first one to be true, implying that omega is equal to 1, it's nonsense, right? Because omega was non-zero argument, and then it was not an even. It's not an integer pi, right? But then in order for this to be 1, I know it needs to be cis 2k pi, where k is an integer. It needs to be even pi, but it's not in the multiple of 2 pi, right? It's a rational number of the argument, of the coefficient. So I know that can never be 0. So what must be 0? Another factor must be 0 so that the product will result in 0. That's the null factor law. So that's a very neat, way of proving it. You can prove it other ways as well using the geometric series, but this polynomial factorization is a very common way to prove, and they actually expect you to show it many, many times. Then I love this problem because it really focuses on what? Deductive thinking, So what you should really think, what you should really consider is the deductive thinking. Where can I find my clue? This one was challenging in my humble opinion because they did not give you many hints. You see, I want you to realize the entrance exam for university, like such as IB or A-level or HSC2, things like that, they are very generous, you see, because they will more of a check whether you've been learning this topic according to their syllabus and curriculum. And they give you even formula booklet for IB, for example, right? But if it's a competitive math, they give you the least number of hints. And it's your job to think deductively. So I call that as will of D. So D's will from one piece, okay? It's a will of deduction, right? So whether you're willing to make extra lines on your own, whether you're willing to make connection from what you have learned previously is what is really to be assessed for mathematics. And that's extensively checked for paper 3, okay? But anyways, we prove this. We must use this because the question is insinuating that I have to use the hence. Right? That's the deduction. And then, every time you're working with the complex number and all of a sudden they give you to work with something with the cosine, what do you have to do? I want you to please think on your own. I don't want you to follow passively. I want you to engage actively, right? Complex number, somewhat cosine. What is it to associate? Very good. You need to associate with the real part. So whatever we have proven, I'm going to check with the real part of that identity. Why? Because the answer somewhat makes a connection with the cosine. And I know I must make some contribution to the real part of that. Okay, so that's great. Should be the real part of the right-hand side must be 0. And you know already that the real part of the cosine is just the cosine, so it's going to be a bunch of sum of the cosine. So let's see. 1 plus cosine 2 pi over 5, cosine 4 pi over 5. Let's go. Cosine 8 pi over 5. So that is lovely, right? And it should be equal to 0. But it's only one more term, so let's write it actually. And cosine 6 pi over 5. So now that's the first will of D. Okay, that's these deductions will, your will to draw any hints from the given identity. Another part that this question checked your will to do the question is that I know I'm given the answer. I know I'm given the answer of what? Cosine 2 pi over 4, cosine 4 pi over 4. I know the answer already, but this is the proving question where you need to get to the answer. You already have a lot of the outcome already. You already have your fruits. What's the fruit of this problem? That I proved using the polynomial that the sum of roots of unity has to be 0, and my answer involves something of a cosine, so I know I'm going to associate with the real part. And I got actually more terms than I got more terms than I need. What I need is actually only for the argument of a 2 pi over 5, 4 pi over 5. Understood? But in the value, I do have it, but I got extra 6 pi over 5 and 8 pi over 5. 8 pi over 5. Maybe I don't like them. I don't want to have this. I want to just have them. So for me, my will, my deduction suggests that I have to change it. So that is required. That is required for you to take the test well, that you are willing to change it based on what hints, what clues you've got. Okay? That's what really they're going to assess you, whether you have a willingness to tackle the problem and solve the question with some hints on your own. Okay, enough with the deduction. So here, yes, for me, I want to make it disappear, and then my best bet is to use the reference angle, because I know that that's same as cosine what? 2 pi minus, that's 10 pi over 5, so 4 pi over 5. But that's the periodicity of the cosine since the fourth quarter, so it's actually the same as cosine 4 pi over 5. In fact, for the last term, it's also same as cosine 2 pi over 5 using the reference angle with the 2 pi. So that is a really great answer. Then what you end up realizing, actually, hold on a sec, that just doubles it. It just makes them all double. So boom, canceling out, it makes them double. Okay? So if you do the rearrange, boom, you got the answer you wanted to have. You do end up having the cosine 2 pi over 5 plus cosine 4 pi over 5 is becoming negative half. So it is your willingness. It's your will to find the fact that I have this identity. My answer involves somewhat cosine. Use the real part. And second part is, I do have a lot of terms. I want to make them disappear because my answer only involves the 2 pi over 5 and 4 pi over 5. Okay? So that's why this question, I think, was harder than the usual other problems because it was involving lack of hints. Okay? We had to come up with. Okay, that's great. So let's have a look at the following form here. Right, given the sys 2 pi over 7, show that blah, blah, blah. Oh, sure. So, I'm given these roots. So what you need to do is to be willingness to use it. Okay, so what I like to do is to use that identity over there. So let's take a conjugate here. So if I take the alpha conjugate, then I'm going to have alpha conjugate plus omega squared conjugate plus omega 4 conjugate. And I want you to realize, what is it? That it is commutative, so omega n to the power of conjugate is the same as omega conjugate to the power of n. And yes, proof is examinable. Okay, so you must be able to prove this. So please do not ignore those proving questions because they are very popular for paper 1 and 2. But yeah, let's use the property. So it's gonna be, that's gonna be cis negative 2 pi over 7. And then, cis conjugate is cis negative 2 pi over 7, but I'm raising to the power of 2. Something to the power of 2, you want to use what, my friend? Yes, you want to use the DMT. So that's going to be cis negative 2 pi over 7 and plus cis negative 8 pi over 7. And yes, please, at this moment, I want to involve with the positive argument because I need to somewhat convert them into omega to the power of 6, for example, one of them. So for me, I know that I need to use the complex equality. What was it? Cis theta is the same as cis. If this was given, then theta must be phi plus 2k pi, where k is an integer, right? So that's what I want to do, you see? So then I know that I need to change into the positive argument to somewhat induce with the positive power using the DMT. So then I will just rotate by just 1 revolution because of the period. So I'm going to add by 2 pi. It's not going to change anything. That's great. So let's add by 2 pi, which is the period. So it's going to be cis 2 pi is a 14 pi over 7. So if you subtract by 2 pi over 7, I got 12 pi over 7. That's lovely. And then this is going to be cis 10 pi over 7. And then this is going to be cis 6 pi over 7. So that's great. But I want you to realize omega was given as a cis 2 pi over 7. And according to the DMT, that's going to be raised to the power of who? To make it 2 pi to 12 pi, I got to make it to the power of 6. So I know that this is going to be omega 6 using the DMT. Very good. That's going to be omega 5. And that's going omega cubic. So that is great. So 653 is what I needed, and we've got it, okay? That is great. Okay, then, let's try to find the B and C. What were the B and C? Those are the coefficient of this complex number, and then what they have said, my friend, I got quadratic equation. I got 2 roots, 1 and its conjugate, according to the question. So I'm very happy. I already have roots, my friend. But here's the thing. This is now your deductive thinking. Quadratic equation, 2 roots given, and I got to find the coefficient and the constant. What do you do? Great answer. They did not tell you to use. However, you need to use a sum and product of roots. Please remember that. Quadratic equation, 2 roots given. I need to work with the coefficient. You need to work with the sum and product of roots. So I do know that alpha plus alpha conjugate, which is the sum of the roots of a quadratic equation, is going to be negative b over the leading coefficient 1. So I'm going to let this to be just negative b. That's it. And then the product is going to be who? Alpha times alpha conjugate is going to be c. Okay? That's great. Sure. So let's use it. So if I add them together, what is it? It's going to be, let's use ascending form, meaning 1, 2, I'm happy. 3, do I have 4? Yes, 5, 6. Oh, okay, that's great. I've got, what is it? Omega 1, 2, omega 6. But here's the thing. This is another deductive thinking. Every time we're working with the roots of unity, what does that also remind you? 2 things I want you to memorize. Sum of roots of unity is always positive 1. Sorry, my bad. Sum of roots of unity is always 0. And then the product of roots of unity is alternating. It's a plus minus 1 depending on the degree. So, okay, we know already this is the roots of unity of z to the power 7 equal to 1, right? That's the solution with this positive argument. We can see that from the roots of unity. Then I know 1 plus omega plus all the way to omega 6 is a 0. So that must be negative 1, okay? So that is actually negative 1. So that is great. So therefore, I know b is going to be 1, okay? Wow, that is great. Okay, so we can actually reduce things down using the property of the roots of unity. Now they have asked me to use the product. Let's use it. So I'm going to do who? Omega plus omega squared, omega 4, omega 6, omega 5, omega 3. Okay, those are the distinct roots. I'm very happy. Let's do the distribution. 9 terms, but it's okay. 7, 6, 4, 8, 7, 5, 10, 9, 7. Only for you, okay? Only for you, my friend. But here's the thing. Yes, it was supposed to be the distinct roots. These were supposed to be distinct roots. What I mean by the distinct roots, I don't bother with omega 7 because that's omega 0, which is 1, okay? And then omega 8 will be omega 7 times omega square, where you know omega 7 is 1. So it's going to be just omega square. Sorry, not square. It's a degree 1, right? So 1 is going to be omega 1, right? Things like that. If you got higher, bigger than 6, such as 7, 8, 9, you can reduce things down. What do I mean by that? Well, first of all, how many omega 7 do I have? Let's highlight. 7, 7, 7. There were 1 from the roots of unity, so that's 3 times 1, so I got 3. Okay? And then let's try to reduce the ones that are bigger than power of 6. So this is 8, that's same as omega 1. That would be omega 7 times omega cubic, so that's omega 3. That's omega 2. Oh, hold on a sec. That's also inducing the sum of roots of unity. So that's going to be, what is it? Do I have omega 1? I think I must have. There you go. 1, 2, 3, 4, 5, 6. That's great because we established that omega 1 to 6, if you add them together, that would become negative 1, isn't it? After rearranging. So I'm going to let this to be negative 1. So that gives me positive 2. Wow. So we found the B and C using the sum and product of roots. And you know what? I am going to make a very extensive video, exclusive video, to actually relate this exam problem from IB into one of the solutions from a math competition, okay? But that's next time. But for this one, let's go. So B is, what was a B? What was a B? B was 1, C was 2. So that's great. So my complex number would be z squared plus z plus 2 is equal to 0. Obviously, what is it? The discriminant is negative, so I know it's not going to have the real roots, but the 2 distinct complex roots. Okay? That is a great, don't worry about that. We already sort of solved that problem, so that's okay. Sure, so cube roots of that, so you know, what I need to do is plug into the polar form here, but we saw in the first part of the question, so here, if you work with the modulus, what is it? Square root of 1 minus cosine square plus sine square. So if I use expansion, that's going to be, what is it? 1 minus 2 cosine plus cosine square plus sine square. That's square root of 2 minus 2 cosine 2 theta. Okay, so that's a straight off trigonometry. So, but for that one, if I factorize by 2 inside, that's going to be 1 minus cosine 2 theta. And I want you to be always thrilled to see the cosine in the pair of 1 because I can get rid of it. So that's going to be using the double angle identity, 1 minus 2 sine squared theta. Right? So if you use it, it's going to square root of 2 times canceling out positive 2 sine squared theta. So that's going to be 2 absolute value of a sine theta. So that's the my modulus, right? That is a great. And for the argument, if I let the argument of z to be, let's say, phi, then tangent phi, you know it's going to be imaginary part over the real part. And I want you to always remember, I want you to tell me this automatically by now, that this is the half angle of a tangent. You should see that right away. Kijun not, right? So it's a negative cotangent, half angle of a cotangent. That's it, no problem. But then I'm not so happy because I wanted to describe in terms of a tangent, how do we easily convert from cotangent to tangent? I do not want you to do the reciprocal, even though that's true. It doesn't really help if you compose it with the inverse tangent. But instead, I know that's going to be negative tangent using the complementary angle, pi over 2 minus theta. And then tangent is odd function. So if you plug it in, tangent theta minus pi over 2 is what I've got. So your argument here must be theta minus pi over 2. So before doing the roots of unity, please put them into the modulus argument form. So my modulus was it was 2 absolute value of a sine theta. That is lovely. But for the argument, it was theta minus pi over 2. So that is lovely. Why is it lovely? Because that's great for me to use the roots of unity. I got to find the cube roots, my friend. Therefore, z1 over 3 is going to be modulus, just put into the cube root. So it's going to be 2 absolute value of sine theta to the power 1 over 3. And then for the argument, that's going to be cis. What is it? The initial argument like that. And then what am I going to add this by? Plus 2k pi over who? 3. And then you got to let k to be who? 0, 1, 2. Those are going to be the distinct roots of the unity of that form. So make sure, my friend, you're comfortable converting between the Cartesian and polar form, especially using a lot of trig identity. That's fine. That's trivial. Yeah, we saw that form. Did you? I just want to see anything interesting because we saw a lot of similar problems like that. So I want to see anything new because at the moment everything seems to be quite similar. Okay. But yeah, I think everything is really similar now. So we briefly went over what. Don't worry about it. It's exactly the same thing as we already have done before. But what we have briefly went over are the 3 things. Okay. Let me give you a summary. So let me give you a summary. If you use a DMT, so you must be able to convert well with the Cartesian and polar form. And for that, I want you to really remember a lot of angular formulas. So typically, you must know reference angle well, complementary angle well, and then double angle well, and then the triple angle, and also the half angle. So again, really working with the conversion between the Cartesian and polar is very often to work with the trigonometric equation revision, trigonometric identity revision. And then the application was higher to lower, that uses the this one uses the z to the power of n plus 1 over z to the power of n is a 2 cosine and theta. Okay? But lower to higher was relying on what? For example, imagine that I wanted to get cosine 5 theta, the angular form of multiple 5, then I'm going to let cis theta to be power of 5 and compare the DMT and then the binomial expansion form. But which part? The real part. Right? We're going to compare the real part. That's what we did for these DMT sort of calibrated questions. But for the fundamental theorem of algebra, sure, if you are given a complex root, please be able to come up with a root. Okay, a conjugate, another root is a conjugate, so come up with a quadratic vector, please. You don't come up with a linear vector for the complex number, always the quadratic vector. So x squared minus twice the real power of the complex number times x plus modulus of z squared. So you must come up with, the quadratic vector pretty easily. Then factorize it, then find the linear, another remaining factor, etc., etc. Another thing with the complex number is that if you are given things like the z plus 4 cubic square linear constant equal to 0, with this type of symmetric equation, what do we have to do? You divide this by z squared, don't you? And then you're going to come up with z squared, 1 over z squared, z 1 over z plus 1 equal to 0, and then you put it into the trigonometric equation, such as a 2 cosine 2 theta, 2 cosine theta plus 1 equal to 0. Then you come up with a cosine. Then if you have a cosine, then you can have a sine. Then you have a one complex root that can lead into the conjugate. So you already have 2. So if you have a complex root, you can come up with a quadratic vector, and you can do the long division for that one. So that's very good, right? So that's another one with the fundamental theorem of algebra. What else for the fundamental theorem of algebra? Nothing much, right? It's very trivial. But for the roots of unity, please remember the formula. What is it? Z to the power of n, cis theta is z, again, cis theta plus 2k pi over n, k is equal to 0 to n minus 1. Those were the distinct roots. And please be able to plot them in the Argand diagram. Okay, so there are many, visualizing question along with the vector. Okay, remember, if you're adding the complex number on the Argand diagram, that's just the sum of the vectors, isn't it? So, it's going to be the diagonal of a parallelogram, right? So make sure you're able to visualize them and add them together. That's a very popular to ask as well. Okay. But also, yes, the sum of roots of unity is always 0, and then product of roots of unity is always alternating term. Okay, always alternating term. So make sure you're able to prove them. Okay, and then use it. So those are the I think the roots of unity that I can do. Okay, but yeah, good luck for the test. Okay, obviously this is. I want you to realize I went over just like this different style of questions in that subject. In order to be good at it, you need to increase the number of practice so that you get used to it. This is really just a taste. I'm not saying that this is everything we need to know. I'm not saying that, but those are like the distinct, sub-distinct techniques that are not very similar from the other ones. But then obviously, if you actually look at it from above, you see they're all intertwined. Okay. So obviously, if you want to be good at it with this technique, please make sure you increase the number of questions to get used to. And there are many, many questions, many resources. Please help yourself. But please know the direction. DMT, higher to lower, lower to higher. Roots of unity, formula, plotting on the Argand diagram, and sum of roots of unity. Fundamental theorem of algebra, bunch of polynomial equations, long division, synthetic division, quadratic factor, etc., etc. Okay? But yeah, that's a quick review on the complex number. I'll see you next time. Thank you.